check. Can you hear that okay? Can you hear this okay? How's that sound?
Morning, Malachi. Don't you guys like the sim session? Get some good stuff out of that. You were there, yeah, right? You were gone, yeah. And you've been simming a lot. What's happening with the club up there? Any news on the club?
Okay.
Oh, really? Yeah. Oh, awesome. Yeah, that'd be great. I'd love to be up there, but I'm too much committed already to much right now. So, but I do want to help out in some way. You know, it's something there. I think that'd be wonderful for a lot of the students. And do you have any students there that are, yeah, interested in aviation?
Yeah.
Awesome. Yeah, that's perfect. If they ever want to, I could talk to I guess, about maybe getting a field trip out to the airport, you know, so they can, you know, they can maybe have a group of students or whatever. See that they're really helpful here. So, morning, how you doing? Okay. Few more minutes. What do you think of the simulator, Malachi?
It's definitely an interesting experience.
Yeah.
I mean, it's just everything you're learning rather than just learning it.
Yeah. You actually apply it. When you get into a real aircraft, that's when you really start, you know, getting an idea of what all the stuff that we've talked about. Then it starts making sense.
Yeah.
You see the weather and you see how the plane responds, all those things they talk about, moving the, you know, the control yoke. You can't really feel it in a simulator, but at least it gives you an idea. This is what it's going to somewhat be like, you know. Okay, so. Morning, how you doing?
One thing is like,
Yeah,
there are a lot of aircraft performance like test their vehicle.
Mhm.
Why did it ask which runway they would be landing? I didn't see the diagrams.
Oh, so and so in the very first part of the SIA, the ground school, there's a an
Well, I was
area.
in those diagrams.
Oh, you were in the diagrams and you couldn't find it or
So
something?
that worked.
Uh-huh.
And then I was at the right diagram.
Mm-hmm.
And then it just had like it didn't show anything about, I didn't read anything about which, uh, failing 714.
Mhm. Can you do me a favor after class? Talk to me about that, and then I'll take a look at it because it could. Some of those I went through. I think it was like 800. I had to create basically 800 questions on there, and I know I goofed up on some of them. And that was probably one of them.
You said I got all the, like most of them right.
Uh-huh.
I haven't passed it yet because I was confused.
Yeah, yeah. No, I'll take it. If you ever come across something like that, let me know. Because like I said, if I had
And there's like 2 or 3 things
that were
kind of related to it.
okay, yeah, we'll definitely look at that. So, all right, guys, let's go ahead and get started. We are on chapter 11 this week. And we are going to be talking about aircraft performance. 11, if you want to turn to pages 11 too. So, so we know that air is a fluid. It's a very light fluid, right? And it's drawn to the earth by gravity. And the density of the air can change based on, does anybody want to take a guess what causes the density of the air to change? Altitude is one, yep, absolutely. What's another thing that can affect heat? Yeah, temperature, yep. Those things can affect the density of the air. And to a lesser degree, even humidity can affect the density of the air. Density is important in aviation because it determines that how well the engine is going to perform. We're basically a biological engine, right? And if we have really dense air, we can breathe really well and lungs work really well. But if you put us up on Mount Everest, all of a sudden we don't do so well. An engine is the same way. The higher an engine goes, in an aircraft, the less performance you get out of it. So we want to get more, obviously denser air is good, denser air. So colder air is denser than warm air. And the lower the altitude, typically the more dense the air itself. Air becomes less dense. Okay, so when air becomes less dense, it reduces the power that the engine can produce. It also affects the prop itself. So when a prop is spinning, it's not able to bite as much air, so it's not as efficient. So it affects thrust on the aircraft. It also affects the lift. So it also affects the lift of the wing because there's not as much air for it to bite into. It's the wing is not going to produce as much lift for any given airspeed on there. Okay, we know pretty much how we measure atmospheric pressure. You've got a little pool of mercury right here, and you've got a sealed tube, and then the liquid rises there. So we know that as this climbs, if this goes up and up, let's say you've got like 30 inches of mercury, we're dealing with relatively higher pressure than we are at, let's say, like 25 inches of mercury. So if I were to take this little barometer up to, right now we're at about 1,000 feet right here is the altitude of Beverly Hills Airport. If I were to raise it up to 5,000 feet, what would happen to this barometer? What would it indicate roughly? Yeah, it would go down because there's less pressure at 5,000 feet. That's pretty much common. Here's the biggest problem with aviation is that there is no standard pressure everywhere. Like the pressure is constantly changing. We live on the earth, everything is changing. You have changes in pressure. When you move from one city, like Reedsburg probably is reading a different, pressure or reading. Let's actually take a look here. So right now in Reedsburg, they're about the same pressure as us, but Madison So Baraboo right now is reading 30.33 inches of mercury. Madison is reading 30.31 inches of mercury. It's not much, but there is a change in pressure. And again, that's because, weather systems, as they move across the Earth's surface, they bring in different, pressures on there. So standard temperature lapse rate. So what a lapse rate is, is the change in temperature or pressure or whatever it is. It's a rate that changes as something else changes. In this case, as altitude increases, there's what we'll call a lapse rate, and you can have a temperature lapse rate and you can have a pressure lapse rate. So in the book there, they talk about standard temperature lapse rate is one in which the temperature decreases at the rate of approximately 3.5 degrees Fahrenheit or 2.2 degrees Celsius per thousand feet. That's important for you to know. I would highlight it and underline it because you need to know what a standard temperature lapse rate is. What that is saying is that in a standard atmosphere, if let's say everything was standard, it was roughly 15 degrees Celsius, and we're at sea level, and the atmosphere was standard, we would be able to measure a drop in temperature at every 1,000 feet by 3.5 degrees Fahrenheit as we rose. Again, that's really important. It's a temperature lapse rate, and that's the standard temperature lapse rate, 3.5 degrees Fahrenheit. A standard pressure lapse rate is one where the pressure decreases at a rate of approximately 1 inch per 1,000 feet. So what that means is if I am at, well, let's see the standard, does anybody know what the standard atmosphere is? ISA? This is something you definitely want to write down. You definitely need to know this up for the test. Yep. 29.92 for pressure. What's the temperature? Yeah. 15. Yeah, it's roughly 15 degrees, like 15.6, I think is where it is, something like that. Yeah, or 15 degrees. It's 50 degrees Celsius, 59 degrees Fahrenheit. For a standard atmosphere. So that you definitely need to commit to memory because you're going to need to know it for the test. All right, so the standard pressure lapse rate is one in which pressure decreases at a rate of 1,000 or 1 inch, 1,000 feet per inch of mercury. So if you look over here, there's this table right here. This describes, this is a standard atmosphere right here. So you have at sea level 0, you have standard pressure of 29.92 inches, and the temperature should be roughly 15 degrees. And at 1,000 feet, we have 28.86 and 13 degrees. Again, 2 degrees per 1,000 feet. That's what we're seeing. That's the temperature lapse rate. If I go between all these, you can see roughly, it's an estimate, roughly 2 degrees per 1,000 feet. With pressure, the lapse rate is roughly 1 inch. Again, it's roughly 1 inch. So we go from 0 feet, which is sea level, to 1,000 feet. We drop an inch there. Now we're down to 28 inches. 2,000 feet, we're down to 27. 3,000, we're down to 26. Okay. So again, that's called the International Standard Atmosphere. It's this right here. That's the International Atmosphere. It's an international atmosphere. Or ISA is what we sometimes call it. So, all right. And again, that you definitely have to commit to memory. So, obviously, when we go flying, we're not going to, it's unlikely that we would actually fly in an ISA or International Standard Atmosphere. So, we have to provide corrections to find out really what our atmosphere is going to be like and how the plane's going to perform. And we'll get into this here in a second. Let's first off dive into pressure altitude. So pressure altitude is the height above the standard datum plane. So that would be the 29.92. Let's see. Basically, in an aircraft, if I was in a plane, to find out what the pressure altitude would be, I would just turn my altimeter. Let's go to the simulator here. Let's dive into the cockpit. Right, so I think we talked to you. Do you guys remember we talked a little bit about the altimeter, how it works there? So right now, the altimeter on this Colesman window, the barometric pressure is set to 30.1 inches. So to figure out what your pressure altitude is for this particular aircraft, you would just turn this right here, this little knob right here, and every aircraft that has a sensitive altimeter on it is going to have this knob on it right here to adjust for a non-standard pressure. So we turn this to 29.92, and we would read our pressure altitude. Does anybody want to take a crack at what that is? What's that? Oh, gotcha. Thank you. Oh, there we go. Thanks for pointing that. Let's see. All right, so
2,700.
yeah, roughly 80. Yeah, 2,780. So that's different than what our actual pressure is reading there. So I think we had like lost this here. See how it went out by about 100 feet. That may seem insignificant, but it could be a problem if you're, at a higher altitude airport, especially if there's a real massive change in pressure and temperature that could cause problems. So again, pressure altitude is the height above the standard datum plane. That's going to be your 29.92, or the state of the ISA there. So the SDP, or standard datum plane, is a theoretical level at which the pressure of the atmosphere is 29.92. We can, when you take the test, you're going to have a document or a figure that's going to show something like this right here. So this is how we calculate our pressure altitude during the test itself. You could actually use just basic math to calculate what the pressure altitude is. So so let's just do that. Let's actually calculate what the pressure would be. So let's say our altimeter right now, the Bear-Rudell's altimeter is 30.33. Can anybody tell me, is that a higher pressure or lower pressure than the international standard atmosphere? It's a higher pressure, which is telling me that the air is denser today than it would be on a standard day. Okay. So, we're reading 30.3. So if I wanted to convert that to pressure altitude, what I would need to do is subtract 29. We take 29.92, which is our standard atmosphere, right, or standard pressure, and we subtract this 30.33. Does anybody know? Is there a calculator at all that can use?
It's native 317.
I'm sorry?
It's native 317.7.
I'm not sure I understand.
Native 317. You subtract that from the pressure.
Oh, 317.
Yeah, native 317.7.
Negative. Sorry. I'm sorry. Okay. Yeah. So 29.92. You're good with me. Okay. So we take 29.92, subtract 30. Whichever the Bear-Rudell's airport current altimeter is 30.33, and you said the.
No, we don't just do the 30.
So yeah, we actually subtract. So let's just do this. So let me just find out here. And you can have obviously a calculator on when you take the test here. So 29.92 minus 30.33, which is the current altimeter at Bear-Rudell, and we get a minus 0.41. So that's a difference. Well, we know that the lapse rate is what for the pressure lapse rate? What's the altitude difference in the per thousand, or the per inch of mercury? What's the lapse rate for pressure? 1,000 feet. Yeah. It would be 1 inch of mercury. Yeah. Okay. So in 1 inch of mercury, the altitude will change by 1,000 feet. Okay, so we know the pressure is higher now. We're going the outside, the barometric pressure outside now is 30.33, so that is above 92.92. So we're feeling denser air. It's going to feel like we're at a lower altitude. Okay, And in this case, it's 410 feet roughly is what we find out. So that was the 29.92 minus the actual altimeter setting here at Bearman, which is 30.33. We subtract that, we get 0.41, and that's roughly 410 feet, right, for the lapse rate, or the difference there between it. So so we apply that to our altitude, and it's going to act right now. Our field elevation, let's just say it's 1,000 feet. It's actually a little under that, but let's say it's what's that?
It's like 940 feet.
Yeah. So I'm just going to do a rough calculation here. So it would be 590 feet. It's going to feel at Bearwood like it's 590 feet on there. So again, you have to be able to do those calculations on the test on there. So, and again, you're calculating for non-standard atmosphere there, or in this case, non-standard pressure. All right, so let's dive into our density altitude on 11.3. Basically, density altitude is pressure altitude corrected for non-standard temperature. Why is that important? You'd think, okay, well, gee, that's just another thing you have to think about. Density altitude has a huge impact on performance of an aircraft. So you can take off, and I can tell you this from experience, you can take off from the airport in the wintertime when it's like, 10 degrees, and your plane is going to perform so much better because there's the air is denser, right? Colder air is denser than warm air. What's that? Yeah, the engine's going to perform better. What else is going to perform better on the aircraft? Cooling, yeah. What else? So you got your engine, propeller, yeah, absolutely. The thrust is going to perform a lot better because you're taking a larger, a colder air is going to be much more dense. So when the prop swings through that air, it's taking a larger bite. It is actually able to propel it faster, so the thrust is more effective. Engines are running better. Also, the wings are producing more lift. You've got more lift for because the air is denser. So density altitude has a huge impact. Normally, most airports don't report the density altitude unless the temperature goes above a certain, like usually like 75 degrees or 70 degrees. Like on a cold day, we really don't care about it because the aircraft is going to perform better than what the book says. But on a really hot day, it's probably not going to perform as well. So we have to know what density altitude is. And that's something you can get. You can calculate this, with a formula, your E6B. But typically they'll actually read it off to you at the airport. It's right there. So air density decreases. Again, you already know this. Air density decreases. Higher density altitude, that is, aircraft performance decreases. So as air density decreases, aircraft performance decreases. Does that make sense? As air density decreases, the aircraft performance is going to decrease as well. Right. Effects of pressure on density. So there is another diagram in here. Let's see. Yeah, this right here. This is a density altitude chart. It basically allows us to calculate density, and you will have this on the test, and that chart supplement. No, not chart supplement. I'm sorry, the testing supplement that you should be able to find in the student portal. There's going to be a figure in there that has this in it, and it allows you to calculate density altitude. So the first thing to calculate in calculating density altitude is, number one, to know what altitude are you at. So right now we're at roughly 1,000 feet. Let's see what what our altitude would be, or our density altitude would be if we go from like 10 degrees all the way up to 100 degrees. So let's start at 10 degrees. We start down here. So notice they've got Celsius there and Fahrenheit. You need to know, obviously, whenever you look at these charts, always make sure you've got the right units, because sometimes it's easy to look. So in this case, we're saying 10 degrees Fahrenheit. And if I go up from here to roughly there, let's see here. So it's not going to change that. So I'll just use the, gosh. Well, okay, just look at the tip of my, you can see the tip of my magnifying glass here. It's pointing at F. Just watch that right there. So as you go up from 10 degrees up to, oh, we'd be way below that. It's not a good example here. Let's go. Let's use 50 degrees right here. So 50 degrees, we go up right here to roughly 1,000 feet. And we actually wind up reading right here, roughly, again, it's going to be below the 1,000 feet because, again, the air is colder. It's colder than standard. So we'd actually read roughly about 800 feet. So the plane is going to perform better than it would with a standard atmosphere. Now, when we go up to, let's say we go up to 90 degrees, okay? And then now let's, so here's 90 right here. I'm going to draw a line up from here to 1,000 feet. The plane is going to appear as though it's going to feel like it's flying at roughly 3,500 or 3,400 feet. That's a big difference because the plane does, what could it do to the aircraft? Does anybody have an idea what density, the air density can do to an aircraft on takeoff?
Increase.
Yeah, increase the takeoff run. Yeah, that's one of them. Yeah, Donnie. Yeah, takeoff distance. Yeah.
Higher stalling speed.
Yeah. It's the aircraft is going to stall because it's not okay. Yeah. Is there anything else that it could affect?
Not just takeoff.
It's possible. Yeah. You could get into a situation. That's something that you hear a lot of out west when pilots are taking off out there that have never flown out at high altitude airports. They'll literally fly off the end of the runway. They're trying to get up in the air. They may actually be able to get off the ground a little bit and then just stay in ground effect. But then they won't be able to get out of ground effect. And they literally go off the end of the runway. That's happened a number of times on there. So again, so this is the tool we'll use to calculate our density altitude. So and again, this you'll have on the test. It's in the testing supplement. You just have to look for it. And again, the testing supplement that you guys have on the learning portal is going to be in the I think the first session. There's like it's not, I think there's like another review or like an area when you first go into the portal. It's the first one, the first segment there. Okay. Let's see here. All right, so drag versus speed. This is C 11.6, page 11.6. So you've got this is a classic drag speed chart right here, and what you can see here as the air speed increases right here, or airspeed increases on this axis and drag increases on this one. So at slow speed, what this is showing us right here at slow speed, your induced drag, and again, that's the amount of drag that we're inducing on the aircraft. If I let's say I want to fly, at a high angle of attack, my flight path is this direction right here. As I, fly along, I have to have enough thrust to keep that plane in the air. There's lots of induced drag right here. Again, the flight path is in this direction right here. So I'll just draw this out here. So there's our flight path right there. We have to have lots of thrust to keep the plane. This is what we call the backside of the curve right here. This area from right here over to this side's backside. So again, at slower speeds, we have to have lots of thrust here to keep the plane in the air. And at some point, if the plane gets too slow, right here, the wings are going to stall. It's going to stop producing sufficient lift, and the plane will just go into a stall there. As we increase our speed, so let's say I start lowering my nose, keep my altitude the same, lower my nose. As we start increasing the speed of the aircraft, lower it, you'll see it gets to a point that's called the LD max. That stands for lift to drag maximum. So you're going to get the maximum amount of lift per drag at this point right here. There's a lot of numbers, a lot of performance characteristics at that point right there that we want to be aware of, which we'll go into in a second here. And then when we start speeding up, you can see two things here. the induced drag decreases. And that makes sense, right? Because induced drag is when I'm flying along like this, the aircraft is creating all the induced drag. We're inducing that by, pulling the yaw back, and the wings are, the air is hitting the wings. That's induced drag. However, when we go past this point, this LD max point right here, induced drag just keeps dropping. So like right now, this aircraft that's flying like this has much less drag, or induced drag, I should say, than this one right here that's flying like this. This has got lots of induced drag. Hold my hand like this out the car window, lots of induced drag, not much, lift there. So it's producing a lot of lift, but it's just creating a lot of drag there. When I lower the nose and fly straight right here, again, induced drag drops off. The other thing that increases, however, as induced drag decreases is parasitic drag. Does anybody remember what parasitic drag is? Yep. Speak up nice and loud. Yeah, all the little tiny things that are, like the fairings and stuff like that. Those are all parasitic drag. That's the stuff that the wind just can't get past. Again, you're going to have, there's always going to be some parasitic drag. It could be just rivets that are parasitic drag. So those things will all create drag. And as you go faster through the air, that parasitic drag increases. So again, our speed increases right here, and you can see our parasitic drag increasing. But again, induced drag decreases. So this produces, when you add those two curves together, this is the curve that you get. This is our drag curve right here. Again, this half of it over here is the back side of the curve, and this is this is just the consider the front side of the curve. This is what we normally fly with right here on this side right here. Again, back side of the curve. And you'll hear pilots refer to the getting on the back side of the curve there in reference, and they also talk about the book there too as well. All right. This is a different type of chart right here. You've got your power versus speed. So again, on the back side of the curve, we are, let's say again, we're at a fairly slow speed right here. The power required becomes greater. Let's see. Yeah, there's your minimum speed, but notice how our power required is higher right here at a slow speed. How you can see how it curves up. That kind of corresponds to this right here. Again, backside of the curve. This is again the backside of the curve. We need lots of power to maintain this, and then at some point the plane is just can't maintain it anymore. You're going to get too high of a critical angle of attack, and it's going to stall. So that's what we're seeing in this. And then obviously we have maximum power available. That's the maximum, basically the maximum thrust that the aircraft can produce. Now some aircraft, they may have certain limitations. You may have lots of thrust, but maybe there's limitations on the aircraft, the airframe itself. It can't support, going beyond a certain speed or something like that. That has nothing to do with this. This is just the maximum power available in flight, and that would be based on the engine, the power plant itself. Okay. Great. And let's see. Yeah, I think we went through this before. That doesn't. Here. So let's here. So let's talk a little bit about angle of climb and rate of climb. This is on page 1117. Angle of climb is refers to how climbing for distance. So if when you think of angles, you think let's see if I don't know if you guys can see these. So let's say we've got a tower over here. I'm just going to hold this up right here. There's a tower right there. We need to climb over that. I can use what's called a best angle of climb to get over that. There's also the best rate of climb. That's different. That's based on time. The angle of climb is based on distance. We want to get over this thing. We don't care how long it takes us to get over this thing. We just need to get over that tower. And you'll find this in a lot of small airports. You'll have like trees at the end of the field or something like that. And maybe you're fully loaded. Maybe the density altitude's really high that day. You need to get over those trees at the end of the runway. So you're going to use your best angle of climb. So to do that, well, the aircraft, typically the manufacturer is going to have that published in the AFM, the flight manual for that particular aircraft, or the POH. It's just a number of, it would be the VX is the actual velocity number that we're going to use there. We actually will see it later in the chapter there. It goes over that. So VX, that's best angle of climb. So we read that, and if it said, let's say like, 60 knots, we would take off. We would want to get our airspeed set at 60 knots, and we want to climb over that. Now, the difference between the best angle of climb and the best rate of climb is the best angle of climb is going to get you the highest altitude for a certain amount of distance. We don't care about climbing, getting up to our altitude fast. If you want to get to our altitude fast and obstacles are not an issue, then we're going to use the best rate of climb. And the best rate of climb is based on, climb per minute. So that's going to be, and this right here, the AOC stands for angle of climb, and ROC, which is rate of climb. Again, VX, AOC is VX in our books, or the velocity speed of X, and the max ROC would be the rate of climb. So again, rate of climb is going to be an airspeed that is typically faster than the angle of climb airspeed. So in that case, we're going to be climbing at a slightly, the nose isn't going to be pitched up as much. We've got full power on the engine, right, for both angle of climb and rate of climb. But our pitch is not going to be as high for rate of climb. And what that means is if I need to get over a tower right here and my rate of climb is really fast, I'm going to hit that tower. If I'm using the best rate of climb that is, I'm going to hit that tower. Whereas best angle of climb, it's going to take me a while to get up there, using a lot of thrust to get up there, but I'll be able to get over that tower when I fly over it. So again, that's the difference between rate of climb, or angle of climb, and rate of climb. And again, the two velocity speeds, VX is what? What is VX? Is that rate of climb or angle of climb?
Rate.
VX is angle. So the way to think of it is X, the letter X has lots of angles in it. So that's a good little memory mnemonic you can use. If you have, if you see the VX, that means it's lots of, it's the best angle. VY is your best rate of climb. Doesn't have as many angles. So that's a thing you can use. And again, you'll need to know that for the test as well. So, all right. Let's see here. Yeah, they go through some other documents or other stuff here. Rate of climb. Let's see here. Okay, so what are some things that might affect climb performance of an aircraft? Anyone want to take a guess?
Air density.
Air density, absolutely. Yeah. What else? How about on the plane itself? Anything on the plane that might affect it? Yeah, weight definitely is going to affect it. Yeah. Yeah, the balance, absolutely. If the balance is out of the CG is too far aft or whatever, that could affect it. Yeah. Drag, yeah, but I mean, you're always going to have drag with everything, right? So unless you're carrying like a, like a banner or something like that, it's not going to change from one thing to the other. But weight does, weight does. And also the altitude that we're at. If we're at a higher altitude airport, is our climb rate going to be higher or lower at a higher altitude? So let's say we're at Bearwood, 1,000 feet, we take off, and then we take that same plane, go out to Laramie, Wyoming, where it's like 7,200 feet, and we take off. Is the climb performance going to be the same out there as it is at Bearwood? No. Why? Yeah, the air is less dense. It's at a higher altitude. Okay, good. Right. Let's see here. So there is, let's see, range performance, and we'll actually get it. We're going to dive right into the charts. They've got a lot of diagrams in there. They're great, but I don't think you're going to see any of those on the test. What I really want to get into is the performance charts and things like that. So let's see, let's show this one. Actually, there's another right here. So this one I will show. This one shows your service ceiling of the aircraft, and this is on page 1199. That is 11-9. So your best angle of climb or your best rate of climb it's going to have some absolute ceiling. The aircraft just cannot keep climbing. I can't just jump into an aircraft and then pitch up for best rate of climb and just keep climbing up to 20,000, 30,000 feet. At some point, for general aviation aircraft, there are things that are going to limit it. The big thing, obviously, is going to be the engine. The engine's just not going to be able to breathe up there. The air is so thin, also the prop is not going to produce enough thrust, and the wings aren't going to perform as well because there's not so much air up there. So there is an absolute or a service ceiling for an aircraft. This is just describing how the airspeed, the best rate of climb speed, changes the higher you go. So you can see here at sea level, for whatever this aircraft is, we don't know, but it's saying it's roughly about 92 at sea level. But as you climb up, that best rate of climb, or best angle of climb, I'm sorry, increases. So if I'm at a 8,000 foot airport, I'm not going to use the published 92 knots. I'm going to use something more along the lines of 95 knots. Seems like a small number, but it can have a huge impact on it. The thing about best angle of climb is it's really close to stall. So you really have to be Johnny on the spot when watching your airspeeds when you do that. So you want to make sure that you've pegged that. Best rate of climb, you've got a little more latitude there. That's typically going to be like another 20 knots or 15, 20 knots, depending on the aircraft. So you've got some latitude there. You can go back and forth if the airspeed is going too fast or too slow there. Right. So range performance. So range performance really has to do with how far you can take the aircraft with any given load of fuel on there. So that's pretty self-explanatory. I'll let you read through there. We're not going to get into that. There's not a lot of discussion of that. Usually it's based on pounds of fuel on there. Maximum endurance condition would be obtained at the point of minimum power or power required for whatever a trip or something like that, and the maximum amount of time that you can spend in the air. So again, the maximum endurance is essentially you've got a gallon of fuel, and you want to get the most time endurance. We're not worried about distance now. We're talking about endurance. How long can I keep the aircraft up in the air with a gallon of fuel? And you're going to reach that maximum endurance condition when you've adjusted your aircraft to for lean out the mixture or whatever, and then you're going to produce the maximum endurance. Maximum range, however, that is going to be the longest distance for that same gallon of fuel. So let's say I want to get maximum range out of the aircraft. So again, that's a setting that we'd have in the aircraft, usually with power, throttle, right? If you have constant speed prop, we'd adjust that. And then obviously mixture, we have to do all three of those things, or at least the throttle and the mixture. We have to configure it. We also have to configure our flaps if that would affect it. And whatever that configuration is will yield to the best range of the aircraft. Again, maximum endurance, maximum range, two different things. Okay, and this gets back to that LV max that we talked about before. So we'll just use this green arc right here. So again, this is the backside of the power curve right there. So on this side, typically the power required, we want the least power required right here. This is 1112. There, figure 1112, 1110 that gauge there. So that dot right there represents your lift drag maximum. So that's the ratio of lift per drag that we want the lift to be as high as possible and the drag to be as low as possible. And that's really right where it's at right there. That's going to give us roughly our maximum endurance, I believe. on there. So not necessarily maximum range there. There's some other variables there, but what you need to know is that the aircraft will stay in the aircraft longer, or stay up in the air longer at this LD max right here. And your range is going to be really going to be extended if you stay in this area right here. Okay. All right. Yeah, some other things to consider too on page 1112, runway surface and gradient. Obviously, a grass strip is going to create more drag on the aircraft lands. Those wheels are going to hit that soft ground. There's going to be a lot of drag there. When you're trying to take off, as those wheels, move along the grass there's drag on that. So you have to overcome that as you apply power. There's a special technique we use when we fly the grass strips, especially short grass strips. We're going to, try to get in the ground effect, stay in it and accelerate the ground effect, and not be touching the grass there. So we actually want to get the aircraft just so it's just above the ground, and then accelerate there and then take off. So again, that's with the runway surface. That's a challenge for us. And you may be landing or taking off at a grass strip. Again, gravel strip is going to have lots of drag. Grass strip is going to have lots of drag. Cement, asphalt is not going to be so bad. It's going to have less drag on the wheels there. And then gradient of the runway itself. If your runway is like this and you've got to take off, obviously we've got to overcome effects of gravity, right, on the runway. So we're going to have to give it more thrust. It's probably going to take a lot more runway to get to actually build up enough speed to take off. So it's a gradient. Actually, we have a gradient downward like this. That's a steep place. Well, actually, I shouldn't take that back. There's places out in Nepal that have really steep runways. But in any case, if the gradient is slowed down like this, you've got gravity working for us, and we can build up thrust really fast and then take off from there. So again, those are going to be performance considerations there. The other thing, water on the runway, we talked about a little bit of dynamic hydroplaning. This is on page 1113. So obviously, water on the runways always increases the, I should say, it always reduces friction between the tires and the ground, but it can reduce the brake effectiveness. Yes.
Go off on a cliff
You could. It is possible. Yeah, it is possible. The drawback there is you'd have to make sure that you didn't get into a spin as you fall off of it. Yeah, but I mean, if the aircraft stays in the proper orientation, yeah, absolutely, you could go right off the cliff like that James Bond movie. I think I forget which one that was, where he drops off it. So it is possible. Yeah. So again, as long as the plane doesn't start a spin prior to building up airspeed, and it happens. And that's a really good point, because when you get into a stall, the first thing we want to do is get a stall. The wings stop producing sufficient lift. The nose is going to drop like that. The first thing we want to do is push that control yoke in, not all the way. We just want to relax our pressure on the control yoke, which is going to cause the nose to drop and increase immediately. And I'm talking immediately. Air is going to start flowing over those wings again, and they're going to start producing lift to keep the aircraft going. So, all right. So let's take a look at some charts here. Yeah, so this is a typical chart. You'll see this, I think, in a lot of Cessna manuals. And we're actually going to walk through a couple of these processes here. So takeoff distance. Notice that this would be a page taken right out of the Pilot's Operating Handbook or the AFM, or Flight Manual. So you've got conditions. This is going to tell you what the standard conditions are. Obviously, they can't print a page for every type of condition that the aircraft is in, but it's just giving you a rough idea of how what the typical aircraft performs at, and then you have to apply that to your situation. So in this case, the conditions for the aircraft, again, this is a short field maximum takeoff distance. At a gross weight, maximum weight of the aircraft is 3,800 pounds. The flaps are 10 degrees, full RPM, full throttle, mixture set, and placarded fuel flow prior to brake release. So whatever if you're at a high altitude airport, this may not be set. The mixture may be set differently. Cowl flaps are open, and the cowl flaps we know. Let's see, yeah, that one does have. But does everybody know what cowl flaps are on the aircraft? The fronts, the engine cowling, they actually open up to allow air to flow through. So that's what those little tiny little flaps that open up to again allow air to flow across the engine. And then the driveway or the runway is going to be paved, level, dry, and zero wind conditions. So that's what they're telling you that when they test this aircraft, that those are the conditions they had for it. Your conditions when you take off are going to be different, and you're going to have to use judgment to get something close to what you think the aircraft performance would be. So yep, they talk about short field technique. Section 4, that's going to be in the manual. There's a section that describes goes into detail of all the techniques you should use there. So in any case, all this to say is you're going to see a lot of charts like this, and they blocked off over half of this. So we'll actually get into let's actually get into one here. See it. Yeah, so you already know this hard surface level dry runway. Obviously, the plane's going to get off the ground. You won't find this in the book, by the way, this chart, this figure right here. Hard surface level dry. The aircraft is going to get off the ground sooner. Wet, long grass, it's going to take longer to take off. Flaps or no flaps. Liftoff point with flaps is going to be sooner than a liftoff point with no flaps. So again, those flaps do a couple things for us. Does anybody remember the two big things that flaps do? I'm sorry. They increase wing area. Yep.
They increase drag and slow you down.
It increases drag and slows you down. What else does it do? No one said that. So that's the big one. It increases lift. The flaps do two very important things. Number one, they increase drag, but they also increase lift. With flaps full, let's say, or partial flaps, the aircraft is going to take off sooner on the runway than it would be later. We use this on like grass runways and stuff like that. So, yeah.
You could take off on ice. Could be faster, slower.
You probably have, if you can control the aircraft, if it's in its solid ice, I would say there's not much friction right between ice and a tire after you get off in a shorter span of time. The problem there with ice is there's no friction. At least on a runway off here, a hard paved runway, you've got some friction to keep your directional stability there. If there's any wind at all on that, or if you have a hard time with left-turning tendencies, the plane is just going to do loops probably on solid ice. So, all right. Temperature right here is a good diagram here. Again, I don't think they have that in the book there, do they? Let's see here.
It says like figure number captures.
Yeah, usually it does do that. So yeah, these are other figures that I had there, but they do describe a couple of things. So if you have a denser air or lower temperature right here, as the airplane comes in, it can use less runway. So if this was less dense air, this plane would actually be using a more runway right here. Again, here's an example of one where the plane is the plane is at a higher altitude airport. It's up here in the mountains, so the air is less dense because it's at a higher altitude, and it's using up more runway. The other thing that can affect it, obviously, is temperature. That's what they were trying to illustrate there. So, you have different surfaces right here. Again, you've got grass surface right here and a paved surface. Okay. In the chart supplement, and you won't find this anywhere. I think you can download chart supplements. Yes, you can. I know You can go to the FAA to download chart supplements. But basically what chart supplements are is they actually have all of the runways in the US, and they give you specs on the runway. So like here, this particular airport name's Jeffco in Colorado, and they've got a runway 11 left and 29 right. It's 9,000 feet long, 100 feet wide. It's asphalt and grooved. So that tells us right off the bat, if I go to that airport, I'm going to know what I'm going to be facing. And as a pilot, you should know these things before you land at an airport. So if I take off from Baraboo, I want to fly to this place, I should know, the runway orientations there, if there's grass runways, whatever. And you can see here, it's got, the grade, that's your slope, your gradient there. And then 5% off. So any case, that's what you're going to find that information in the US chart supplements. Again, that's something that FAA produces there. Okay, tire pressure. We don't think about that, but tire pressure can affect it can affect the drag. So if you have high pressure, you've got your wheels are pumped all the way up, you're going to be able to roll a lot easier than if the pressure of the wheels was let down quite a bit. So also it affects the hydroplane of an aircraft. So I think talking about there. So I think they go into a little bit. If it let's see, so you can actually calculate the hydroplaning when hydroplaning begins on a wet surface. I don't think you're going to actually see that on the test. It's good to know. Yeah, they actually have the formula here on there to calculate. Again, I'm not going to go into it. Just know that hydroplaning is a potential issue, especially on wet surfaces. Let's see here. Okay, another thing that affects performance is tailwind and headwinds. So do you think it would be better to have a headwind coming in for a landing or a tailwind? Yeah, you want a headwind. Okay, why is that? Why would you want a headwind? Yeah, reduce the speed. You want to touch down at the slowest speed possible. So having a headwind to keep that aircraft going slow, I mean, to you, it's not going to look any different other than, it's going to feel like, you're coming in a little bit shorter, you've got a good landing or whatever. But if you have a tailwind, again, we are saying the air, we're in a parcel air up here. The aircraft, has to maintain a certain airspeed in that air. But if the air is also moving, it's moving the aircraft much faster. It may be coming down at the same angle as an aircraft with a headwind of 20 knots. But because the air is moving that it's in, with a tailwind, it's pushing the aircraft along. So we wind up taking up a lot more runway, and I mean a lot. 10 knots doesn't sound like much, but if you have a 10 knot headwind and you go around and land in the opposite direction, it's a huge difference. You eat up more runway. It's more challenging coming in because the aircraft it's harder to judge how much runway you're going to use because you're moving so fast on the ground. So the ground speed, obviously, with a headwind is going to be lower than the ground speed with a tailwind. Okay. All right. So again, here they talk about here a headwind that is 10% of the takeoff airspeed reduces the takeoff distance by approximately 19%, 20%. So if it takes me, 1,000 feet to take off in my airplane, if I have a headwind, a 10% headwind, I'm gonna, it's gonna decrease my distance down to 800 feet to get off the ground. So they have has a huge impact on there. So that's what this is kind of talking about here. So, yeah. Yeah.
Check out the inside.
Yep. Mm-hmm. Ground speed you're talking about? what your ground speed would be, or?
Your indicators.
Yeah. Mhm.
Uh,
So yeah, your ground speed is what you're talking about, right?
okay.
Yeah. So let's say you're coming in for a landing. You want to know if you were driving if you had a car below you that was mirroring you. You want to know how fast that car's going, right? Is that what you're saying? Yep. So no, you don't. No, you can use GPS. Most, like you get like ForeFlight, like, I mean, there's dozens of devices you can get, but just basically tablet, smartphones. I've got this one. I've got, ForeFlight on here, and it actually tells me what my ground speed is. So I could use that. Generally speaking, you're going to use your best judgment. You're not going to be referring to ground speed. Although when you have like a real high headwind coming in for a landing, it's actually kind of fun to see what your ground speed is. Because in some cases, like you can take the Cessna 150, we can take that up, and we can actually fly backwards. It's a really weird sensation, but if the winds are sufficient enough, you can get the plane slow enough in the air, and the ground speed will actually be negative, and you'll actually be going back. Sorry, say
I'm
again.
able to do that with my RC.
You can do it with your RC,
Yeah.
yeah.
Look back.
Uh-huh. Yeah, so that's a perfect, good example for it. Yeah, you should actually videotape this or record it sometime. Yeah, I see there. So, all right. So let's jump to page 11-18. So performance speeds. I'm not going to go into. We've already talked about these. So there. Here. So performance speeds, again, we've talked about all of these, but let's just quickly review them. True airspeed is the true airspeed of the aircraft. It's not what you read off of the airspeed indicator. That's the indicated airspeed. And that's next. Indicated airspeed is what is actually showing. Anytime we see the word indicated, it's talking about what you're seeing in the cockpit. When you look at the gauge, that's the indication it's showing there. The calibrated airspeed has to do with the corrections of the aircraft, due to calibration errors or whatever in the aircraft, the way it's set up in the aircraft itself. Equivalent airspeed, we don't use that much. Let's see, VS0 and VS1. Those are two big ones you need to be aware of. First off, VS, what does VS stand for? Without looking at the book. What does VS, V speed, VS stand for? Anybody want to take a guess? Said vertical speed. But V stands for velocity, yes, but what does the S mean? Stall speed, yes, stall speed, yep. So the VS0 and VS1, those are numbers 0 and 1, not VSO. But when I look at VSO, if you look at it, it's the down here, again, this page 11-18. VS0 is the calibrated power off stalling speed, or the minimum steady flight speed at which the aircraft is controllable in the landing configuration. So that's with everything hanging out. When you look at that VSO, think of everything hanging out, like the gear, the flaps, everything. It's a landing configuration. Okay, so we come into the land, we're going to drop our gear, we're going to drop our flaps. That's VS0. Okay, VS1 is the calibrated power off stalling speed. Again, it's another type of stalling speed with basically everything in retracted, the gear up and things like that. But it's really what those numbers represent are configurations. So VS0 is an aircraft configured to land. VS1 is an aircraft configured for steady flight or whatever, cruise flight. But you may have VS2, VS3, VS4, depending on the type of aircraft. If you're flying like some heavy metal, it's going to, there may be several different speeds because they've got spoilers, they've got flaps, they've got slats, they've got all these things that affect the performance of the aircraft. So we're only, as general aviation pilots, typically we're only concerned about VS0 and VS1. VSY, what is VSY? We just discussed. Donnie. Best rate of climb. What's VX? Best angle of climb. Yep. Again, remember X is that the character X has lots of angles in it. So think of best angle of climb. Then the VLE, I won't go into those. You guys can read that stuff there. Probably the most important one really is the maneuvering speed there. That's VA, and that one, I don't know how to create a memory environment for that, but it's just VA, and that's the design maneuvering speed. And then you've got VNO, which is the normal operating, and VNE, which is pretty easy. That's never exceed speed. So let's dive into the performance charts. Okay, so let's see, maximum freedom. That's 20. Here it goes right here. So this is on page 1119. So, you know, obviously with all this stuff gets to this point right here. So we need to take off. We have to, in order to fly our plane effectively, we can't just wait for a standard atmosphere day to come up. It just, you know, you'll probably never have that in your life. There'll never be a day when, you know, the pressure is 29.92 inches and the temperature is 15 degrees Celsius. It just won't happen. So we have to use performance charts to help us determine whether our aircraft and the loading on the aircraft and the weather conditions are safe for the aircraft to take off, and then also determine if the aircraft is, you know, what kind of performance it's going to have, you know, how well it's going to climb and things like that. So let's see here, maximum rate of climb. This is a typical performance chart. Again, you're always going to see this conditions. You've got flaps up, gear up, the RPM you set to full power, 2,600 RPM, and that's, again, for this particular aircraft. And this, we don't know what it is. They're just using this as a sample here. Cowl flaps over the standard temperature, and again, you've got you know, the weight of the aircraft with the sea level pressure of pressure altitude. I'm sorry, 4,000 feet here. Climb speed here. And this just gives you some numbers here. This is going to make more sense when we actually get some of the samples, the examples here. So, which is on the next page. So, if you go to 11-20. All right. So let's actually walk through one of their sample problems. So there is a term called interpolation, and let me just grab a pen. Oops. So does anybody know what interpolation is? So interpolation has to do with basically coming up with an estimated value between two other values. So let's say I've got all right, so let's say I have a value of 500. It can be for anything, altitude, whatever. And I've got a value of 1,000 feet, or 1,000. Let's just say it's feet. Okay, so you got 500 feet and 1,000 feet right here. So interpolation, what that means, it refers to is, you know, if I say the altitude that you're going to be at is going to be between 50% the difference between 500 and 1,000 feet. So what would that be roughly? 50% of the difference between 500 and 1,000 feet. 750 feet, right? That's interpolation. So if I say it's, you know, you'd have to, you know, use a calculator here, but let's say it's 25%. So 25%, or let's say it's 20% from 5 to 1,000 feet, or 500 to 1,000 feet. What would that be? Yeah, 600 feet. So again, you're interpolating based on another value. So right here, if I say, you know, the 60% or 20% difference, it's going to be an increase of, you know, basically 100 feet. So that's what you're doing. You're interpolating between. And the reason we use interpolation with these charts is because you can see here, that the, you know, we can't come up with all the different numbers here. So oops. You can't, there's, you know, that they could produce a chart for every one of these conditions, but it would just take up, I mean, it would be a book that, you know, it's like, you know, maybe a couple thousand pages long. And we just want rough ideas of how well the aircraft is going to perform. Again, in this chart, we're calculating takeoff distance right here. So it's based on a maximum weight of 2,400 pounds, flaps at 10 degrees down, full throttle, paved level runway, and zero wind. So if we're given you know, a problem here, let's see here, did it actually? So, okay, yeah. So in your book, it's sample problem 2 in the book there. We're talking about takeoff charts there. So pressure altitude is 2,000 feet. Outside air temperature is 22 degrees. Takeoff weight is 2,600 pounds. And headwind is 6 knots. Obstacle weight is 50 foot obstacle. This is a typical problem that you're going to have to solve when you take the written test on there. So, and they say refer to this figure 123. Oh, that's actually, sorry. Let's back up a second. So let's go to sample problem 1 here to figure out. That was a little bit easier to start with that. Let's go here. So that is referring to this diagram. So sample problem, again, density altitude charts. Just did this. It should be pretty easy. So use a density altitude chart to figure the density altitude at the departing airport. Use figure 1122. That's this figure right here. And again, we've already done this, so it should be pretty easy. Your airport elevation is 5,800. Outside temperature is 70 degrees Fahrenheit, and the altimeter is 30.1. With those things given, we need to calculate our density altitude. So let's see, the first step, first compute the pressure altitude conversion. Find 30.1, again, our given altimeter setting is 30.1. So we find it over here, 30.1 inches of mercury there. And you'll see on this, and this, by the way, this right here is, you're going to have this on the test. They'll actually print this out. This eliminates the need for you to do math in your head with it. You can just look at this chart right here. So to find the pressure altitude conversion of this, you look for 30.1 inches, which is this right here. And then you read across from that minus 165. So under the altimeter heading, let's see. Yeah, the altimeter. Yeah, that's the very good. So you're going to find 165. So it reads 165. Therefore, it is necessary to subtract 165 from the airport elevation. So our airport elevation is what in the sample problem? What do they say our airport elevation is? I'm sorry, what? Are we on the same page there? This is page 1120, and we're looking at density altitude charts. The sample problems number 1. What's the airport elevation? 5,883 feet. That's the airport elevation. That's what is given to us. So to get our pressure altitude, then we would subtract that 165 that we came up with over here from that 5,883 feet to yield a pressure altitude basically of 5,718 feet. Let's see, and then next locate the outside temperature. On the scale along the bottom of the graph, outside temperature is what for that problem? 70 degrees Fahrenheit. So I'm looking for this. There's 70 degrees right there. And again, that's what's given to us, 70 degrees. Draw a line up to the 5,718 feet. So we draw it up to 5,718 feet. Which is right here. Again, they've done this problem for you right here, that red line. I'll go up there, and About 2/3 of the up. Draw a straight line across from here, and that is going to be our density altitude right there. So it's our density altitude is not 5,000 feet or 5,800 feet. It's more like 7,000 feet. This question gets answered wrong all the time on the test. And again, you need to be comfortable working with these. I'd go through a couple different problems, make sure you understand, how to do it. But the fact that the book gives you this sample problem and that red line right there, that's essentially what you would write on this, right? You would go up here and draw that in there. Does that make sense for everybody? Yeah. All right, good. So here, takeoff chart. So let's take a stab at that takeoff chart there. So, and this is using, it's this one here. Okay. So sample problem 2. This is on page 11-20. The problem, sample problem is on 1120. The chart we're going to use, however, is on the figure we're going to use is on 11-22. And this is what the figure should look like right there. So, okay, with given these items, pressure altitude is 2,000 feet. Okay. Outside air temperature is 22 degrees Celsius. Again, always watch for units there because they go back and forth between Fahrenheit and Celsius. They want to make sure that you catch those things. Takeoff weight is 2,600 pounds. Headwind is 6 knots. Obstacle height is 50 foot, which is pretty standard. Usually when they give you a problem, they'll say that the obstacle height is usually like 50 feet, which is not uncommon here. So. Okay, so if we read the instructions here, refer to figure 11-23. That's this figure right here. The chart is an example of combined takeoff distance graph. It does several things. When you look at it, so first off, it's this section right here takes into account the pressure changes and temperature changes. This one right here takes into account the weight of the aircraft, this section right here. This one takes account of the headwind or tailwind components. And all of these things I'm telling you right now are going to affect the performance of the aircraft. In this case, the takeoff performance. You'll see very similar charts to this for landing performance as well. This right here is, again, looking at the obstacle. You can have from a 20-foot obstacle all the way up to a 50-foot obstacle that you have to contend with. So again, this is a classic example of a performance chart. It's telling you what to expect under differing, temperature and pressure conditions, differing weights of the aircraft, differing headwinds and tailwinds and obstacles. Okay, so let's actually walk through this whole problem here to make sure that we understand it. All right, so pressure, we start at outside temperature of 22 degrees, again, Celsius, Fahrenheit here. So there's Celsius right there. We start at 22 degrees Celsius right there. We draw a line up from that to our pressure altitude, which is 2,000 feet. So and you see this is kind of a slanted line right here. So when we hit that, we stop right there. So again, 22 degrees to 2,000 feet our pressure altitude right there. Okay. And then we draw a line straight across until we get to the next area, which is the weight of the aircraft. And notice that these lines, they're just guidelines. What you're going to do is you're going to draw a line parallel to those guidelines until you get down to, in this case, the weight of the aircraft. The weight of the aircraft is 2,600 pounds. So we follow it down to 2,600. We stop there. We draw a horizontal line straight across until we get to the wind component side. So this is going to be your headwind or tailwind. And notice you've got the dashed lines, that's indicating a tailwind. And you've got the solid guidelines here that are the headwind. Those are most of the time we're going to want to take off or land in a headwind. So again, it stops right here. We're going to now, let's see, we've got a headwind of 6 knots. We're going to go down roughly to 6 knots right here, and then we're going to stop and then draw a horizontal line all the way over to the next one right here. And this is the obstacle height. And this, in this case, the obstacle height is 50 feet because they've given that to us in the problem there. We're going to draw a line. Again, we follow the guidelines up, and we come up finally with a result of around 1,400 and what would that be 1,450 feet, something like that, or what is it? Yeah, it looks like I think it's 1,400 feet. All right. So that's again this chart. This is our takeoff distance. So our takeoff distance under these conditions is going to be roughly 1,400 feet. Now, to understand these charts, the best thing to do is to practice working with them. Create some sample problems. Make sure you understand how they work to get the proper answers. And then obviously when you take the test, you're going to want to go through there and practice the test questions as well. And there's a lot of resources as well on the internet that actually go through that stuff. Any questions on any of that stuff? Okay. So your landing charts, takeoff distances, they're pretty much use the same type of methodology there, where you've got a group that covers a certain, like in this case, the air temperature and pressure. It's going to be covered under this chart right here. It then leads to the next chart. In this case, you're dealing with the weight of the aircraft. And notice that these are with certain settings on the aircraft. We're just they're making the assumption that you're full throttle, you're lean for the appropriate fuel pressure or whatever. The flaps are up, things like that. So they're making certain assumptions. So if you have if you're taking off slightly differently, whatever, you're going to have to take that into account. I think for the FAA, when they give you the questions, they're going to make the assumption that the aircraft is going to be configured the way it's listed in the chart itself. You should be able to do that. Okay, let's see. Short field takeoff distance. Again, that's a slightly different one. Let's see here. Yeah, so this one isn't. It doesn't use the graph like these right here. This is a typical graph. It's going to use a chart. So again, instead of trying to follow the chart, which I think is a little bit easier, you can get through it a little bit easier. You're actually just using these charts. So what we do here again, we read the top, flaps 10 degrees, full throttle, paved runway, 0 min. Okay, well, what's our weight of the aircraft? So in this case, let's say we're at gross weight, which is 2,400. So that's easy. Now we're going to be focusing on this area right here. So what's the temperature out? Well, the temperature is 20 degrees Celsius. So then now we're going to be in this column right here. And again, weight is in here. We've got our temperature right here. So now we know we're somewhere in this area. What's the pressure altitude? Okay, so now we determine our pressure altitude using those charts I showed before, the table there. We would determine what our pressure altitude is. And now we're narrowing it down. So our ground roll is going to be about 1,230 feet, and total to clear a 50-foot obstacle. Again, what they're talking about here is you're taking off from the runway, moving along at 1,230 feet. You can rotate, the plane will take off. However, if you have a tree at the end, to clear that tree, you're going to need roughly 2,295 feet is what they're saying right here under those conditions. So to clear that, you need to have at least 2,225 feet, and that's with a test pilot with a brand new aircraft. So you as a pilot, and everybody that flies planes knows this, that once an aircraft comes out of the factory, it starts the performance starts declining a little bit. Not a lot, but it will over the years. And so as that performance declines, you're going to have to kind of pad these numbers to be safe. So in this case, I would probably pad that with at least another 500, maybe 1,000 feet to make sure that I can get my plane. Yep. Not necessarily. Like if I would say Bearwood doesn't have any 50-foot obstacles. I've got the Cessna 150. Let's say I'm going to take that off. The only thing that I'm really concerned about, obviously, I want to make sure the engine's running. I want to make sure it's got oil. I want to make sure the weight and balance. This is something you need to do every single flight. You do have to calculate your weight and balance. There's programs that do that, and it doesn't take very long at all. But outside of that, you've got 5,000 feet of runway here, and the plane may only take 500 feet. to get off the ground. So I don't really need to do the performance on it. Now, if I was taking that same plane out to Laramie, Wyoming, or someplace that has a higher altitude airport, yeah, I would probably do a performance calculation on it, at least a little ahead of time, just to know on it. You as a private pilot or a student pilot, you're going to have to know this stuff, and you're going to have to show your instructor that that you know how to calculate performance on every single flight. They're going to want to see that. They're going to want to know that you know how well the aircraft is going to perform, even though you know you've got plenty of performance to take off from this airport or land at this airport. But so to answer your question, it depends. So as a student pilot, you should be practicing it every single time. And again, there have been a lot of situations where pilots have gotten themselves in hot water because they didn't calculate performance. And I would say there's been a couple of times where I've been really close. A long time ago, I took off. I was a very young pilot, so arrogant, and I took off from the airport with an instructor, another instructor. There was a 50-foot obstacle. It was a very short runway, and we just barely made it over the trees. It was scary. So I mean, the stall warning was actually just starting to go off as we were passing over the trees. So again, that's one of those situations that had I sat down and done the performance calculations, I probably taken off there. So, or I would have lightened the load of the aircraft. So, all right. All right. So there's cruise power settings tables. Do you guys kind of understand how these tables work? Essentially, just going through them. Does that make sense? Any questions on any of this stuff? So I think the biggest one was that, using these tables right here, these charts right here. Again, you're just following it. They almost always have some sample problem, and then they give you the answers on it. So that's something to look out for in the test. If you don't remember how to do this, just look for those sample problems in the books. The manufacturers, aircraft manufacturers, always have some sample problems in there. Okay. Let's see, fuel time and distance. Again, this is using the same type of chart. Start with the temperature, you go up to the pressure, altitude, and then you go across and you can read all these different things, fuel time, distance calculations there. Normal climb, 100 knots, fuel time to climb distance. Again, nothing unusual here, the same type of chart. It's just going to give you different things. So again, start getting comfortable with those, and then when you get to the point where you're taking the test, and be comfortable in looking at those charts there. So this one, again, it was kind of like those other ones, like these right here. You always start, usually you start on the left-hand side, and you're going to start with, like, in this case, the temperature right here. And you can see, it's kind of hard to see here, but you've got a dashed line there. So they give you a problem right here. The example problem is cruise pressure altitude is 5,000 feet. Cruise outside air temperature at cruise is 16 degrees Celsius. So again, you can see it starts here at 16. It goes up to pressure altitude of 5,000 feet. Right there's our 5,000 foot guideline right there. Stops there, goes straight across, and then you can kind of read the rest of it. So that's how those charts work. And you have to be really comfortable, because you're going to be dealing with them a lot. Here's some other ones there again, different types of charts there. This right here is a crosswind component chart. So if, given, let's say, actually, let me just see if we do here. Yeah, they do have the figure 1031 in the book there. Yeah, so if you have, let's say you have a 30, well, let's say you get a 10 knot headwind that's off, like 30 degrees off of the nose of the aircraft. You can actually break it up into headwind component and crosswind component. So the headwind, obviously, the headwind component is what is heading in here and directly into the flight path. The crosswind would be the wind that would be effectively pushing it from the side there. So and this is important because most aircraft have a limitation on how much of a crosswind component they can deal with. So if it's a really strong crosswind component, they may not be able to compensate for it. and you wouldn't want to take off and stuff like that. So this just breaks it apart. So what I would do if it's 30 degrees off of the front of the aircraft, let's see, I would go down to first I start at 30 degrees and then drop down to the 10-degree line right here. And then I draw these lines out. I can see that the headwind is going to be roughly, 9 knots. And the crosswind component is going to be roughly, 5 knots or something. Yeah. Does that make sense for everybody? So you start up here with the degree difference off of the nose there, and then you drop down until you get to your crosswind, whatever the wind is outside. So if it's reporting, let's say Baraboo is reporting winds at 30 knots at 360. Okay, so that's 30 knots, and it's out of the north. So it's 10 degrees. Our runways are oriented 01, which is just off of north. 001 is actually 10 degrees, pointing 10 degrees north, right? So 360 degrees, our wind is actually coming this way at 360 degrees, and it's at 30 knots. So I would just go right up here to 10 degrees. It's off the nose by 10 degrees, and then you just follow this until you get to 30 knots, and then you can see your head. And the other question.
I'm just like, so the crosswind component chart is marked as 1031. It's 1131.
Oh, okay, yeah.
And here it says refer to figure 1032, when really it's 1132.
Okay, a good point. Good point. Thanks for pointing that out. So, yeah, I don't know why that was a mistake.
It happens surprisingly often.
Yeah. This this is a great book. It's the one that we choose, but they do have some flaws in it. And I think they do have they've just released a new one of these, but since you guys have the printed one, you don't have the the updates on there. So, or do you? Does everybody's book right now? If you look at the crosswind component chart, does it say 1131 in there? It says 1031. Okay. Yeah. All right. So that's still then. Hopefully they'll get it fixed at the latest version. If you download, I think the latest PDF, they may have corrected that. So, all right. Again, landing distance charts. I think we talked about that. Again, you have your conditions. The flaps are lowered, your power off, zero wind, and again, they're basing it on gross weight. Obviously, at gross weight, if I reduce the weight quite a bit, is it going to take more or less runway to land if I reduce the weight of the aircraft? It's going to less weight. Again, just use common sense. Yeah, so of course it's going to use less weight. So, okay. All right. So let's take a 10-minute break, and then we're going to jump back and get into weather theory and weather reporting. Oh, good. I've got a bunch of updates too for this. At some point, I'll probably actually be down there on Tuesday. Okay. Okay. Yeah, I probably won't be able to stop over because we do this all day. Yeah. Oh wow, that's great. They got this big. Are you familiar with yeah. Big pictures for the kids, which is awesome. Like somebody. No, I haven't. Yeah, I talked to him on the phone. Okay. Really super nice guy. Yeah. Really excited about that. Yeah, that'd be fantastic.
I got it. Yeah. Both well, actually, all three of them supposedly, well, two of them are, they're in the shop now. And the other one is going in. And I love to take a swing down there. It's like a 20-minute flight. It's yeah, it's very fast. Actually, the 150 is probably good. The cheap is not bad. The tweak is not. That's what I said. But yeah, I'll probably be doing hopefully a lot of flying there. We'll be doing I think in 2 weeks. We'll probably be taking a lot of students too. Somebody will have a chance to fly them. Some of them may have to sit in the back seat, so it's just and maybe a couple. They fly with me, I probably take 50, but take one at a time. So yeah, I think so. Yeah, they'll be able to kind of put two together with all the stuff they're learning and apply it to real life. Improvement, yeah. So it's a A&P. So there's Brent, Scott, yeah. So Scott can do the work on it. Brent has so there's an A&P, which stands for Airplane Power Plant Mechanic. Okay, and both of them are A&Ps, so they can work their operations in one place. But then to return it to service, you need what's called an inspection authorization, and that's like an additional one that Scott's working toward his Brent already has it. So he can look at my plane, he can sign it back so that it's sign it in so that it's so that I can actually now take it out, and fly it. Whereas Scott, just work on it. We'll get to the point where so it's the transition from jets, which to me is just amazing that it goes reciprocally. But there's a lot of different, same type of paperless like that. I mentioned with jets, the people were just one time, but they still have to keep track of everything. But anyway, he's he'll definitely do his inspection authorization at some point. So yeah. That is just one of those things, I guess, with aviation. And that's probably a good thing because now we have safety and overall excellent aviation. Yeah. Mm-hmm. Yeah. If plumbing, if something. Yeah. Mm-hmm. Glass air. Mm-hmm. Oh, cool. Yeah. Take a long time. They are beautiful airplanes. I'll tell you what. That's exactly. You think about that glass air, that's what it is. You sit basically on the floor. The seat's just a little, maybe a couple inches above it, off the floor. But they go. Really tailwind. Those are. There's a guy in the field who was fascinated last year. He had built these what we'll call tailwind. Basically, it's a tricycle gear aircraft. Really stubby wings. It's two-seater, and hardly any. The power plant was maybe like 160 horsepower, but we could easily get 230. Which is just insane for a small plane with that much speed, that low of horsepower. Yeah. What's this? Oh, the glass air. Yeah. We were just talking about that. They are absolutely awesome aircraft.
They were talking, can you do all the maintenance on your airplane to build it?
If you build it, yes, you could do your own maintenance on it.
You said that I inspected it.
I don't. It's a good question. I don't know if you can return it to service yourself. I think you have to have a person with what's called an inspection authorization to allow it to be returned to service. But you can do all your own maintenance on it. if you build it. I think you have to have somebody else do it. I know when the aircraft actually, after you get done building it, you have to have it certified. I mean, the FAA has to come in, but it's the after you do your annual inspection or whatever, I think you have to have somebody else come in and just verify it, what you've done is correct. All right. All right, guys, let's dive back into this. We've got 2 more chapters to cover today. So now we're going to dive a little bit into weather reporting and things like that. To understand weather, we kind of need to understand some basics about weather itself. So they talked about the composition of the atmosphere, basically 21% oxygen, 78% nitrogen. This right here kind of gives you an idea of how the different areas of around the Earth, the layers, let's say, of the atmosphere itself. So you've got the troposphere, which varies in height based on where you are. Like toward the equator, the troposphere is going to be much higher. At the poles, it's going to be much lower out there. And then stratosphere is typically from 20,000 to 160,000 feet. We obviously do all of our flying, and the vast majority of it in the troposphere. And the vast majority of that is in a very small window down here. It's less than 10,000 feet for general aviation planes. Like the high flyers, the commercial airlines will try to fly in the stratosphere. A lot less air. The totally different characteristics when you go from the troposphere to the stratosphere. Not as much weather up there. The conditions there are usually a little more stable than the troposphere. The vast majority of weather is located in the troposphere, below that 20,000, and the vast majority of that is even located within like 6,000 feet of the ground. That's where you're going to find most of your weather. So if you want to avoid weather, typically you want to climb as high as you can. So they talk a little bit about here lapse rate. Inside the troposphere, the average temperature decreases at a rate of 2%. That was what we talked about before. The standard lapse rate is about 2% per 1,000 feet. So if the temperature at the surface right here is let's say 10 degrees Celsius, at 1,000 feet, it's going to decrease. So it's going to be like 8 degrees Celsius at 1,000. And if we go up to 2,000, it's going to be, the temperature up there is going to be even less than. So again, we use that lapse rate that we talked about before, that 2 degrees Celsius lapse rate. It's a standard lapse rate. Great. Let's talk about atmospheric circulation. So the Earth is obviously rotating, right? And because of that, you get these circulation patterns. This is a circulation pattern with the Earth not moving at all. So what happens is, let's say the Earth just freezes, and we can survive it. So you've got lots of heating around the equator. Because the Earth is heating there, the air rises, and what happens is it does this circular pattern where it actually travels up to the cooler air, and then it cools down. The air descends as it cools, and then it flows down to the equator again, heats up, and you've got the circulation pattern right here. But the Earth is rotating. Because of that, because it's rotating, it changes these patterns a little bit, but we still have the same circulation pattern right here. We see this right here. Let's see here. Yeah, they talk about it. I think figure 12.5 actually kind of goes into the different circulation patterns. That's on page 12.4. That talks about how the Earth modifies the static. If the Earth was still right here, it kind of modifies this. And you get these little patterns where the Earth is because you've got in this area up here does not spin as fast as this area right here. If I put a pin on the Earth and we watch it rotate, this pin, if it starts right here, as the Earth rotates, is going to cover a lot more distance than if I put a pin on the Earth up here. This is going to travel much slower. And because of that, we get these circulation patterns on that. Let's see, it's this right here. This is the diagram there. So these are much shorter. It's not traveling as far up there. So it develops these circulation patterns right here. Again, that's because the Earth is rotating. Look at those lines there. I think we all know that obviously we've talked about this before. You've got, if you took a column of 1 inch of air and you ran it all the way up to space, and put that column of air on a scale, it would weigh 14.7 pounds. Okay, we all know that. I mean, we feel it right now. We don't notice it because we feel 14.7 pounds per square inch on us all the time. So we're used to it. If we go up in altitude, that pressure is going to keep decreasing on there. We're going to start feeling it, maybe 20, 30,000 feet. We really notice it. We'll be able to breathe. What's your question?
Is there anything to your knowledge that you notice that it's scary?
Don't know. I suppose maybe.
NASA did make designs for those.
So here at 18,000 feet, we look here at 18,000 feet, our pressure drops almost in half, so 7.4 pounds per square inch. And that's at 18,000 feet. Okay, you guys? So 3 cell circulation pattern, again, this is what we're just talking about. That's because the Earth is rotating. This area right here is rotating much faster than this area up here. Again, we get those circulation patterns there. Okay. Let's see here. Okay, differences in air density caused by changes in temperature result in change in pressure. And this has to do with the Earth heating and cooling. As the Earth heats, the pressure is going to decrease, right? You've got air that is expanding. So if the sun hits the Earth, and really, the sun is really what drives weather on the Earth, on the planet Earth. It's like when that energy hits the Earth, it heats up the atmosphere and it expands. So we have either higher or lower pressure, but it's going to modify the weather on the planet there. If you've got a rainstorm that comes over, it's going to cool things. It's also going to increase humidity. That's going to affect it as well. So again, differences in air density caused by changes in temperature result in a change in pressure. That's an important one. Again, that has to do with the sun rays hitting the Earth, heating the atmosphere, and causing it to change the pressure there. The atmosphere is almost constantly in motion as it strives to reach equilibrium. That's a good statement there. I've got this highlighted in the if you go download the PDFs for this, these statements are all highlighted that I'm talking about right here. But this is on the lower right-hand corner of 12-5. So let me read that again. The atmosphere is almost constantly in motion. So the atmosphere around the Earth is always constantly in motion. That means that the pressure is changing, the temperature is changing, winds are changing, things like that. So the atmosphere is never static. You're not going to, maybe have a few days out of the year where the temperatures that are exactly the same, the pressures are the same, but eventually it's going to change. And you just don't see a constant, pressure and temperature and everything like that last for weeks on end. Because again, the Earth is in motion, the temperature of the sun hits, the rays hit the Earth. The tilt of the Earth also affects how much heat the Earth gets as well. Obviously, we know that because in the summertime it's really hot, and again, it has to do with our Earth, rotating, or actually the poles shifting a little bit there as we rotate around the sun. So again, let me read it one last time just to make sure I drill it home. The atmosphere is almost constantly in motion as it strives to reach equilibrium. So the one thing about the atmosphere, there's atmosphere, is it does try to get to, equilibrium with, if you've got like a high pressure area here and a low pressure area here, you're going to have high pressure trying to go to low pressure. It's going to flow through there. And then, low pressure may be sucking in, air from the high pressure or whatever. But it's going to try to get to equilibrium so those two areas are, equal, right? So you've got, maybe this is over Minnesota and this is over Wisconsin right here. This is high pressure in Minnesota and this is low pressure in Wisconsin. Well, the high pressure in Minnesota is going to, if the earth wasn't moving and there's nothing else affecting it, that high pressure would try to equalize. Here's the problem. The earth is rotating. You've got all these other factors and it creates weather, which is incredibly complex. And so you have these things going from, trying to get to that equilibrium, but because all these other things are taking place, the earth's rotating, whatever, it's never actually going to get to equilibrium. It's going to try to, but it's not. Okay. Altitude and flight. Let's take a look at that one. We've already talked about this. This right here, this is a typical, layout for a altimeter right here. These sealed aneroid cells. These are all connected right here, by the way, but it's basically a balloon right here. And as the balloon increases or decreases, it changes our little indicator right here. Obviously, an altimeter in an aircraft has a lot more gears and stuff like that to display it correctly, but this gives you an idea of what happens. As the outside air pressure here increases, these wafers, these little aneroid cells here, they're just basically little wafers, they're going to compress, and that's going to indicate that, you got a higher or lower pressure there. So, okay. Pressure gradients. This is something you'll see in weather charts. So now that you know a little bit about weather, you'll probably want to go online. You can go to NOAA. There's a weather.gov site you can go to, and they have a lot of charts that you can view, but they use gradients a lot. So in this one right here, we're seeing what's called, it's just a high pressure area right here. You've got low pressure. And then you have these, indicators here of what the pressure is. These are in millibars, by the way. They're not in inches there, but maybe this is like 30.1 or something like that. This drops down. That would translate to, but again, you've got low pressure here. So you've got high pressure trying to move toward low pressure, but it's a gradient. It's when you look at a relief map. You guys all know what a relief map looks like. When you look at a topological map or something like that. It shows like a mountain. It's got the lines like this, these gradient lines right here. It's just trying to show you the difference in altitude. This is essentially what these are right here. And again, you're going to see these everywhere in aviation when you look at various maps. What we're really primarily concerned with is high pressure and even more so low pressure. Low pressure, as a general rule, always brings poor weather. Okay, always, you're going to have like storms and low pressure. You generally don't see that with high pressure. But you see it in low pressure. You see a lot of storms. The hurricanes are all low pressure. The eye of a hurricane is like super low pressure. You actually feel it. When we get tornadoes, it's usually in a low pressure system. Right. And because of all of these changes here, let's see if I can find this. Again, at Denver, you may have a pressure. Well, first off, let's talk about this. So, does anybody know how high Denver is in feet, in terms of feet, roughly? Is that? Yeah, about 6,000 feet. Yeah, it's the mile high. The mile high airport. It's basically a mile high, which is roughly 6,000 feet. And because of that, the pressure, station pressure at Denver is 24.92 degrees. On a standard atmosphere, that is, it would be 24.92. And at sea level in New Orleans, it would be about what standard atmosphere would be, 29.92. So again, there's less pressure. Again, this makes sense. We're not learning anything new here. At 6,000 feet, the pressure is going to be lower than it would be, let's say, at New Orleans, which is sea level. Okay. And again, we're basing it on, in this case, a standard atmosphere, which, again, does everybody know what a standard atmosphere is? What are the numbers for a standard atmosphere? 29.92, and what for the temperature? 15 degrees Celsius. Yeah. Good. Okay. So obviously, those are going to affect the performance of the aircraft and how we fly there. So let's see here.
Conversion of Celsius to
You'd have to work it out. Yeah, I don't know. It'd be easy enough to calculate, but there's I'm sure a way to do that. Just for your knowledge, I guess, when you take the test, they do have charts to convert Fahrenheit to Celsius. So if you do need to do it, you can try to do it by memorizing a formula. The simplest thing to do would be to look in the testing supplement for a conversion table. They usually have that in there. Yep. 1.2, yeah, that sounds right. Yeah. Yeah. And you can try to remember that. I can't, yeah, honestly. But yeah, if you can remember that, then you can convert, on the fly if you needed to. Yep, 32 degrees Fahrenheit, which is freezing, equals 0 degrees in Celsius. And then you can actually figure out what the formula is by going up to the boiling point, which is 100 in Celsius and 210 in Fahrenheit. And based on that, you can kind of create your own, conversion. But again, that's way too complicated. You don't need to do that. Just look at the charts on there. So most average people become somewhat impaired at an altitude of about 10,000 feet. For some people, impairment can actually occur at as low as 5,000 feet. This is nothing new. Again, we know this from people that climb Mount Everest. There is, and when they say impairment, they're not talking like you're instantly going to become unconscious at 10,000 feet or 5,000 feet, but your vision does taper off a little bit at 5,000, around 10,000 feet, especially at night. Your nighttime visual acuity drops dramatically. And you can even go up and test it. Sometimes people fly with somebody over 5,000 feet. If they've got oxygen at night, just take a hit of that oxygen and you're going to see a huge difference in how bright the stars become, after you take in that oxygen. So again, it does affect everybody. It's something you need to be aware of. Okay. Let's see. That's altitude in the human body. That was one of them. Yeah, here's again pressure, altitudes at sea level. Obviously, the plane's going to perform really good at sea level. When we move that pressure altitude up to 8,000 feet, this plane's going to need a lot more runway to take off. Again, that's what we went through this last class or the last session. Then we talked about performance. That's where we have takeoff distance, charts and things like that. We need to have that, and we need to know what the weather is so that we can calculate those things. Circulation patterns for high and low pressure systems. So let's say here's Minnesota right here, and here's Wisconsin. You may have a high pressure area. Air flows out of a high pressure system, and it flows counterclockwise. Clockwise. So high pressure systems rotate clockwise. Low pressure systems rotate counterclockwise. Okay. So they've got, and I think they call it cyclonic and anticyclonic for high pressure, which really confuse things. But again, clockwise for high pressure systems, counterclockwise for low pressure systems. And air has a tendency to flow into low pressure systems. Again, like a big vacuum cleaner sucking in air. High pressure it flows outside of it. Think of it as a mountain of high pressure, a mountain of air, and a valley of air. You oftentimes hear weather forecasters use the term weather trough or something like that. They'll say a trough. And that's, again, we think of a trough, it's something that's like a valley, it's down deep. That's where a low would exist. So when they say trough, they're talking about low pressure, and it's usually like an area of low pressure. So if you hear them say that sometime now, you'll know what that means. Okay, here's isobars. Again, this is showing millibars instead of inches of mercury. But this, here, a trough of low pressure. You're not going to find this in the book. It's not listed in there. But you've got the isobars that tell you you've got relatively high pressure over here, but as you get closer to the center of the low, you've got lower pressure here. Just like this one right here. Again, this is the cyclonic motion of a low pressure system. Again, we've got the isobars, showing the changes in pressure right here. They don't have a label, but so this is a pretty strong low pressure system, 960 millibars. It's pretty low there. The stronger, the deeper the low is, the stronger the forces are in it. So the faster the rotation. If you have a really strong low, if you have a super strong low, you have like a tornado or a hurricane primarily. If you look at the eye of a hurricane, it's extremely low pressure. And that's because all of the air is just getting sucked into the center of it. And hurricanes rotate really fast. Okay, so again, a really strong low in the center of a hurricane is going to produce, more weather because the pressure gradient is so much steeper. So that's what we're kind of seeing, with this. So when you think of low pressure, think of a hurricane. A mild low pressure we get through here all the time, but it just brings in kind of bad weather, not a hurricane. Okay. High pressure, again, this is the anticyclonic. So this is going to, typically the wind currents move in a clockwise form here. So if I'm south of a high pressure system, I would expect, winds out of my east right here. Okay, if I'm south of it. If I'm north of a high pressure system, I'm going to expect winds out of the west blowing this way. Okay, so that's what they're showing here. And you can do the same thing with a low, here. So if I'm traveling north, if I'm just south of a low pressure area right here, I'm traveling north on this, I would expect winds out of the west from there. And this, you can count on it. Every single low pressure the system that comes in, you can prove it. Just go online, look at the weather charts, and you will actually see that the winds are always out of the west, on the south side of the low. On the north side of the low, they are out of the east. And again, opposite for a high pressure system. This is what's called a high pressure ridge. It's kind of hard to see here, but this would be like a ridge of high pressure. So we talked about trough, that's a low pressure, refers to low pressure. A ridge is just, again, it's like the topographical features of a map. If you have a ridge, you'll be able to see that ridge on there. Well, this is just doing the same thing. Instead of, showing terrain, it's showing the pressures. Yeah.
Why do they rotate counterclockwise in low pressure in a high pressure area? Why do they rotate clockwise in a high pressure and counterclockwise in low pressure?
Because of the earth rotates. And again, this gets back to, if I go right here, yeah, this, because of this right here, it's the Earth's Coriolis force, and it's going to affect.
They flip.
Right, when you get a good point, yeah. So when you go, if this is in the northern hemisphere, in the southern hemisphere, it's just the opposite. So if you're flying down there, those are rotating the opposite direction of the high, and the high is rotating the opposite direction. But up here, since we're in the northern hemisphere and we're primarily concerned with the U.S. because you're getting a private pilot's license in the U.S., we're going to focus on that. But it was a good point. I'm glad you brought it up because that is, that's what the Earth does. It creates those circulation patterns, and it does affect those, the high pressure and low pressure. Okay. Great. Yeah, this talks about the pressure gradients. So again, the air in a high pressure system wants to travel to the low pressure, but again, you've got air moving, anticyclonic, or I should say counterclockwise in a low, and clockwise in a high. And because of that, you get the air doesn't, the winds don't always follow that pattern. They kind of flow in a low pressure system. They're going to actually twist a little bit, and more, the winds are going to point more toward the center of it, whereas in the high pressure system, they're going to point more toward the outer point. They'll still, they'll still be somewhat circular, as they'll still circle around the high, but they're not going to be a perfect circle. They're going to actually, the winds are going to kind of go off to the sides there as the high rotates there. Yeah, and here, this is a good diagram. They show this right here. So again, the high pressure, you've got that counterclockwise rotation here. You've got the air flowing a little away from the low outside. You can see how it's not staying in line with that isobar right there. With a low pressure, just like I said before, if as the low pressure system rotates, it also brings that air in, so that the winds are going to be pointing more in toward the center there. Not a lot, but they will be there. So, and then this is just let's get talking about there. Oh, yeah, so this has to do with, fuel. And so, let me see here, patterns. Yeah, they actually described it, and this is on page 11.7. Wind patterns in the northern hemisphere, the flow of air from areas of high and low pressures deflected right. Yeah, so that was what I was just talking about, the anticyclonic, all that stuff there. All right. All right, so now I'll start getting into the things that affect your flight itself. So let's go here. So convective turbulence. Okay, first off, what causes a balloon to rise? What can cause a balloon to rise? Air pressure. Okay, if you have low pressure, that can cause it to rise. Yep, that's one thing. What else can cause a balloon to rise?
Which balloon are you talking about? Hot air balloon or helium?
Just any balloon.
Okay. Then it would be the lighter air pressure and hot air balloons due to the heat.
Yeah.
Causing it to expand.
Uh-huh.
And helium balloons due to the heat.
Yeah. So what I'm looking for there is the hot air balloons. So hot air balloons, when you fill a balloon up with hot air, it has a tendency to rise. This is called convective flow. Right here, you've got air moving up. So you can see these little bubbles of hot air. And if you could actually see the atmosphere when you're out flying, you would see, it would look like a boiling pot of air. If you could actually see it, little bubbles of air coming up, rising up off the ground. So what happens is the sun hits the earth, it heats a patch of ground. Maybe it's a freshly plowed farmer's field, and that ground heats up. Well, it heats up the air above it. That air then rises, and you get this bubble of air rising, right? And when you're flying, if you're flying low enough to that, you're going to see, you're going to run into this turbulence here. These little bubbles of air that are coming up, and it could be from a parking lot that's painted, freshly painted black, or maybe they just laid out asphalt. It's really hot over that little parking lot. That's going to modify the air mass, that local air mass. It's going to create turbulence, and that's why we encounter turbulence. And typically that extends up, that turbulence extends up to the base of your cloud layer. So, and then above that, and you'll find this, when you start flying, if you get above the clouds, it's usually very smooth. The clouds, just all they're doing is they're showing you where the turbulence is. When you see like real puffy clouds, like cumulus clouds, they're really puffy and stuff like that. All they're doing is they're really showing you where that turbulence is. It's actually showing you the air where it just kind of stops or whatever. It's a great tool to have when you're out flying. If you want to avoid turbulence, you look for the tops of those clouds. You fly 500 to 1,000 feet above them, or 1,000 feet above them, and you'll stay in smooth air. Whereas if you stay below them, and in some cases you have no choice, you have to stay below, because maybe this is complete overcast, and we can't, as VFR pilots, you wouldn't be able to fly above that overcast layer. So you'd be stuck down there, and you'd have to deal with the turbulence. So again, the sun heats the earth heats up, and it heats air around it. The air rises, and we get turbulence. That's called convective turbulence. Okay, this is another type of air movement. Yeah, Theo.
So I was wondering, black heats. Black, when the sun hits black, it heats up, causing the air to heat above it, causing the air to become less dense. So why aren't runways white instead of black?
Anybody want to answer that? You have an idea why? They certainly could paint them white. Yeah.
One of the reasons why check also it's like a spirit.
Yeah, definitely. It melts definitely melts it off. That's probably not the reason they do it. It's more for cost. Yep. Go ahead. Yeah, you can build a lot of runways are made out of cement, which cement is much lighter than asphalt. So they still, it may cool down, it actually much cooler, let's say in the summer months, but they probably contend with more ice. I think it's more out of practicality that they whatever the runway is. So
Yeah.
what's that?
white reflects light.
Yes,
And
yeah.
when you're coming in the land, you
Yeah.
don't.
All right, yeah, perfect, yeah.
Also, center lines, white on one lines, seems like that's what changes.
Yeah, it would change it. So yeah, it would affect it. So, all right, so let's take a look at this next one right here. This is a sea breeze and wind circulation pattern that we typically see on coasts. It could be coast of Lake Michigan, it could be on the ocean coast or something like that. But the typical, convection currents, I think this is a convection. Let me see here. All right, so well, let's just take a look at this here. So obviously, water has a much, how would you call it, stronger or less? I guess we have stronger thermal inertia. And essentially what that means is water doesn't change temperature very, very easily. It takes a lot more energy to change the temperature of water than it does air. And that's why, like, when you go out to Lake Michigan, it's always just cold in Lake Michigan or Lake Superior. But even though the temperature outside may be 100 degrees, that temperature of the water is still cold. It's because the water is so much more dense than the air. So it doesn't change temperature. You need a lot more energy to change that. So anyway, what they're showing here is this typical circulation pattern. If there's no winds or anything like that, it's just going to start developing wind, because what you have here is you've got the sun heating the ground right here. And as it heats the ground, it heats the air rises, and then it wants to get back to equilibrium. It wants to, once it cools down, it wants to drop through, here. And so what happens is you get the circulation pattern when you're on the coastal areas there, where you've got, again, heating of the air rises, and as it moves, it cools down, and then it starts this rotation here. So you get this air flowing like this. So if I was landing at an airport right here, I would expect some good sea breezes, in the area. So that's what they're referring to here. At night, it just reverses the flow. So usually, because again, the ground cools a lot faster than the water. Again, the water is, if it's like 55 degrees in the day, it's probably going to still be 55 degrees at night, that same night. However, the ground, though, because there's no sun hitting it, it's not producing any more heat. Well, now the ground is cooler than the water here, and so the water descends, or the air descends here, and it goes across the land. It starts heating up when it hits the water here, because the water now is warmer than the land, and then it rises and it creates this flow pattern. So again, this is sea breeze and land breeze wind circulation patterns. Again, we see them a lot. This is a good example here of of heating from the sun. You've got a parking lot, you've got warm rising air. If you've got a runway over here, well, you're probably gonna have some turbulence there. And it might be just a bump or something like that. On really hot days, you can definitely feel those bubbles of air, if you will. And then literally, again, it's like think of the atmosphere on a hot day as like a pot of boiling water. You've got little bubbles of hot air moving up. Your aircraft is going to be just hitting those, and it's not like it's throwing around. In some cases, it can be pretty severe, but the vast majority of time when you're flying, it's just going to be, the plane is just going to be doing this, just kind of bounce around a little bit there, because that comes in, and the plane comes into land. So this could be your flight path right here. This kind of a green line or a gray line is there. That would be your normal flight path, but because of the turbulence, it's going to affect your flight path. So the other thing, water is much cooler. So you could have, in this case, they've got the parking lot right next to the flight path right here. And then you've got this pond of water, which is during the day is going to be much cooler than the parking lot. So now you've got a double whammy. You've got the bubble of hot air moving up. You've got the sinking cold air, and it's going to push it down. So those are the types of things that we have to deal with as pilots. So if you get in a situation like this in real life, what you would probably want to do is just adding power and kind of maintain your flight path. With wind, surface winds, you get also what's called eddies. So if you've got winds here, in this case, this wind is moving across the terrain here. It hits these hangars right here, and it creates these little circular patterns. These things that it's kind of a chaotic mess of wind. It's flowing all over the place. Those can be tricky to deal with sometimes on takeoff. Again, it's just basically, it's another type of turbulence. I think they call it orographic turbulence, but it's basically, it's, you know, because of the terrain there and, you know, buildings. When you fly into big cities, you'll, you know, feel the turbulence from the buildings there too. Depending on the winds, if there's no wind, you're not going to feel anything. It's going to feel, excuse me, totally smooth there. So, all right, let's see. I'm sorry.
Next slide there.
Oh, what was that? Hold on.
Next figure,
Which one was that?
year 1216.
Okay, yeah. So yeah, that's so let's go here. There we go. Let's move it up there. Okay, so then this is a type of terrain-induced turbulence. So if I'm this again, this is why we need to know what the weather's doing. If let's say I'm flying out west and there's an airport right in this area right here I want to get to. As I fly this way, if I don't know what the winds are over here, I may think that, well, I can just land there. Well, if the winds are really strong over this mountain peak right here, they develop those eddies there. You can see these eddies there, just, you know, the wind is all over the place, and come in and land, and it could be a, you know, kind of a tough landing. So you have to be prepared for it. You want to know what the winds are, you know, on the windward side, and then the leeward side. Obviously, you want to know what the winds are here at the airport. This airport's right there. There's a place out in I think it's Wyoming. It's called Rock Springs, Wyoming, and they always have such strong winds out there that several airlines send their pilots there to do practice crosswind landings. So the winds are always consistent, and you know, it's out in the mountains area, in the mountainous area there. So there's a lot of turbulence. You get these eddies and things like that. So it's consistent every day. They just have strong winds. So pilots have to get really comfortable doing crosswind landings and, you know, dealing with turbulence and stuff like that. That was probably the worst turbulence I think I've ever flown in. And I not had a seatbelt on, I would have probably gotten knocked out in the plane. It was that bad. Okay, low level wind shear. So when you think of wind shear, you think of, well, let's talk about what is shear. Does anybody know what shear is? Can anybody explain what shear is?
Something going.
Yeah, something going one way and another way. So I can be shearing, you know, two pens right here. So this is shear right here. So I'm shearing these two right here. And with wind, it's the same thing. Wind shear is just that. It's, you know, you've got shearing, you've got a level, let's say the wind going this way, and down here, maybe the wind, you know, going this way. And we oftentimes, when you think of shearing, sometimes we mistakenly think that the wind has to be going in opposite directions. It really is just relative. So if wind shear can also be wind going, you've got two levels of wind here. Let's say one at 1,000 feet, one at 500 feet right here. This is a 500-foot wind direction and speed. At 1,000 feet, it may be 20 knots, and at 500 feet, it may only be, you know, 1 or 2 knots or something like that. That's still considered wind shear, okay? Even though the direction of the wind is the same, that's what we call wind shear. There's a difference between those two. So, and there's a very specific term for, you know, wind shear. Low level wind shear is commonly associated with passing frontal systems. When you get the low pressure system, usually they have like fronts that move in temperature inversion, and a strong upper level winds greater than 25 knots. I think let's see, actually define it here. I think wind shear can there's a very distinct number for that we refer to that classifies it as wind shear. But again, you could, you know, have wind shear at 2 or 3 knots, although it's really hard to see. But what we're talking about there is that the general, you know, the wind is changing in direction. Okay, so you could also have at 1,000 feet and 500 feet, you could also have both the 500 or 1,000 foot level. Maybe that's 10 knots, but it's pointed north, and the 500-foot level, it's pointed east. That's still considered wind shear. Because again, you've got, you know, air going north here at 10 knots, and below that at 500 feet, it's still going 10 knots, but it's in a totally different direction. That would also be considered wind shear. And it has, again, huge impact for pilots, because when we're coming in, we're looking at an airspeed indicator. If all of a sudden the airspeed changes, and we could get into a stall situation that could cause a problem. Landing, we have to add power. It did happen, I think, down south. It was a big. This is back in, I think, in the 70s or even 60s. There was a wind shear accident, and it wound up being pretty devastating for the airline. There was just a massive amount of wind shear jet. It was a commercial jet. I think it was a 727 or something like that. That came in and landed. They had a lot of wind shear, and basically they tried to pull up out of it and didn't want to crash it. So wind shear is a big problem, and with small aircraft even more so. Okay, so most severe type of low level wind shear is a microburst. So microbursts typically occur around thunderstorms. We're going to get into that a little bit more, so I'm not going to talk about it too much here. When we talk about thunderstorms, they are literally weather factories. They produce all kinds of weather, and we see them all the time here in Wisconsin, but in other states, for those of you that are in other states there. But yeah, thunderstorms occur a lot, and they are, like I said, they're literal weather factories. They produce just a tremendous amount of dangerous weather, and we always want to give them a wide berth when we fly around them. We don't want to be anywhere close to probably about 20 miles at least. Let's see. So microbursts, yeah. So they do talk a little bit about the speed lifespan. And this, I think you do see this on the test. The lifespan of a microburst is about 5 to 15 minutes. That'll probably be on the airwritten test. And it's during which time it can produce downdrafts of up to 6,000 feet per minute and headwind losses of 30 to 90 knots. What that means, a headwind loss of 30 knots. Let's say you're flying a Cessna 150 and you're coming in to land. The landing speed on the Cessna 150 is about 40 knots. If you lose that headwind, 30 knot headwind, the plane is going to stall. It's just going to stall unless you get or push the nose down and recover. But the problem is when you're coming in for landing, you're really low to the ground, right? So when point down, you're obviously going to hit the ground. So again, that's why we're so concerned about like wind shear and microbursts. Okay. Let's see. Yeah, so we talked a little about this. This is page 1212. Wind and pressure representation of the surface and weather maps. Let's see here. First there. First. Yeah, it's this item right here. So again, they're showing millibars of mercury. This is typically going to show inches of mercury. Although I will say a lot of aviation charts do use millibars, but they convert those over to inches of mercury as well. Those are the isobars. Those are the lines right there. They kind of show you the change in it. If you look here, this is 1,008 millibars, 1,012, 1,016, 1,020. It keeps going up. So we know that we're going from the low pressure to the high pressure is probably somewhere up here, again, just by looking at this basic recipes. I guess I will show you maybe this real quick, and then we don't have to cover it later on. So microburst, you get this, is basically a really strong downdraft. And when the air descends like this, it's obviously going to push the aircraft down, but it has two effects on the aircraft that are either heading into it or heading out of it. So as you're heading into it, a microburst or a downdraft right there, the aircraft performance is actually going to improve because you have a slight headwind. So the aircraft will actually start, getting slightly better performance. When you hit the downdraft itself, that's when things turn sour. So obviously you've got the pressure of the air pushing the aircraft down. But now as you fly through that downdraft, you're on the back side of it, you now go from a headwind on this side to an increasing tailwind. And that's where pilots get into trouble when they deal with a downburst or a downdraft, that is, or a microburst on there. Okay, there's another diagram there. It shows the exact same thing. And they are strong. Microbursts can be very intense. Usually we see them around the edges of a thunderstorm. Really powerful thunderstorm, but you can see there are cases where there was a downdraft in the day. I mean, when you have all this air, hot air rising, the earth heats up and the air starts rising, then at some point that air has to come back down to earth, and that's when you get those downdrafts. Yes.
How much altitude
Well, it depends. I mean, if it's a 6,000 foot per minute, you're going to lose 6,000 feet in a minute. Not to mention all the other things that are preventing you from getting down. So yeah, you could easily get pushed into the ground if it's a strong enough microburst and you have a small aircraft. You just don't have the thrust to get out of it. So in a situation like that, if you do get yourself caught in a microburst, full power and abort your takeoff first off, because there's no way you're going to get down safely, and especially in a really steep, strong microburst on there. So, but yeah, it can be pretty tremendous if you're in one. So, like I said, they said 6,000 feet per minute, but again, you have all these other factors too. The airplane may not be performing as well, and if it's a little hot day or whatever. So, I don't know if that answered your question there, but yeah, it's something that you don't want to play around with as a pilot. If you encounter one, you basically want to firewall the throttle and go around and land it in another airport. You don't want to take a chance of landing it in something like that, because it's they've got wind shear sensors and basically they detect microbursts at a lot of airports. They're that concerned about that. FAA spent a ton of money on those things because they don't want people to encounter that stuff. And if they do, they want to at least alert them and get them out of the area there. All right. So again, this is our ISO bar is to reveal the pressure gradient of an area, high and low pressure areas. We'll see a lot of those if you go online again to weather.gov. You can see all kinds of charts that show this, and I really encourage you to go online, maybe watch a weather report, and they'll almost always talk about low pressure systems and high pressure systems. Okay, relative humidity. That's another one of those things that affects aircraft performance. This is a 1220. This is page 1213. We talked a little bit about relative humidity. So I've talked about this before, but in the summer months, when the air heats up, it has a greater capacity to carry water. So here's the thing about water vapor. The more water vapor you have in a parcel of air, you would think, well, you guys tell me, do you think a parcel of water, air that has water vapor in it is going to be more dense or less dense than air that is completely dry?
Less dense.
Okay, less dense. Say less. Say more. Less. It's actually less dense. Yeah. When you have hot, humid air, if let's say you have just a parcel of air that's at 70 degrees and it's humid in it, and you have a parcel of air that is 70 degrees and it's completely dry, the one that's humid is going to be less dense than the one that's completely dry. Okay, doesn't seem logical. Part of the problem with that is because when we were kids or even adults, when you get those hot, humid days in the summer, people say, "Oh, the air is so heavy." That's not the case. The air is so light. That's why you're having a hard time breathing. So on a hot, humid day, when somebody comes up to you and says, "Oh, the air is, it's so heavy today, I can't breathe," it's not because it's heavy. It's because it's light. It's just the opposite of that. And that's what you have to unlearn with when it comes to humidity. Hot, humid air is much less dense than even hot, dry air or cold, dry air. So there's also a couple of things too with humidity. I think they talked about this here. Yeah, temperature dew point relationship. Okay, so let's talk about that because that can be confusing. So at sea level, air can hold. They talk about this gets into this. You don't have to remember these numbers right here, but at sea level pressure, air can hold 9 grams of water per cubic meter of air at 10 degrees Celsius. But look at this. As the temperature rises at 20 degrees, we can hold 17 grams of water per cubic meter. And again, that's at 20 degrees. And we go to 30 degrees, that's like 100 degrees or 96 degrees, something like that Fahrenheit. It can hold 30 grams of water. So what that tells me is the hotter the air is, the more capable it is of holding moisture. And it kind of makes sense when you think about it. In the summertime, you get those hot days, those hot, humid days, and we get those intense thunderstorms. Lots of water is dropping, and you can almost see the humidity in the atmosphere. It's so dense with water. Whereas on a a really cold day, the water vapor is like cold dry air actually is not going to hold much any, but cold air itself, because it's more dense, it's colder, it can't hold as much moisture. And there's some things that happen in the weather that kind of help us identify or show about that. So when we look at the weather reports, in the wintertime, for instance, we've got this polar mass moving from Canada, and you've got this tropical air or air moving from the Gulf of Mexico. That's got lots of moisture in it. When it hits that cold air, what happens is the cold air can't hold as much water vapor that's in the air coming from the Gulf. And so when those two systems hit, we get a snowstorm. You've got cold air, you've put lots of water in there, it's going to produce lots of snow, because again, you've got cold air that's enough for it to snow. But you've got all this moisture coming from the Gulf of Mexico. We've got some of our strongest snowstorms, when those two systems collide. You get the cold polar air that comes in from the north, and you've got again that moist tropic air that comes in from the maritime air that comes in from the Gulf, and hits that, and we get again thunderstorm or snowstorms. But what they're talking about here is they're getting in trying to set up the stage for understanding temperature and dew point. So a parcel of air can only hold so much water, whether it's hot or cold doesn't make a difference. It can only hold so much. So what they're saying here, again, let's read this again. So 2 grams of water per cubic meter can be held by a parcel of air that's 10 degrees Celsius. Anything above that, let's say the water vapor increases, it actually condenses and turns into rain or snow. Okay, so when the water vapor increases beyond that 9 grams, per cubic meter of air at 10 degrees Celsius, you're just going to get some sort of precipitation, because it can't. That parcel of air can no longer hold all that water vapor; it has to release it, and that's when you start seeing, snow or rain or something like that. Again, think about this again. So you've got cold air here, and again, cold air is, they're saying here this 10 degrees Celsius, which is relatively cold. It can only hold 9 grams. And at 30 degrees, we can hold 30 grams in that same parcel. So in cold air, again, it's not that it's dry, it's just that it can't hold so much. So the point, this is what we call the temperature dew point. So the temperature, when I say the term temperature, we're just referring to the temperature of the parcel of air. So if this is this parcel right here is 9 degrees, or at 10 degrees Celsius, the dew point for this at 10 degrees Celsius, let's see, would be the point at which, well, so let's see here. So, well, let's say this parcel of area is 20 degrees Celsius. The dew point is the temperature at which the water condenses in that parcel, and it starts reducing or dropping like precipitation. Okay. So in cold air, right here again, let's look at this again here. So 10 degrees Celsius can only hold 9 grams of water vapor or water itself per meter. Again, if we try to add more water vapor in there, it's just going to shed it as rain or snow or something like that. So it's just going to fall out of there. And again, that's where we get like snowstorms or rain or whatever. But the temperature is the temperature at which back up here. The dew point is the temperature at which it's going to start, releasing the water vapor in the form of precipitation. Okay, so again, you have the temperature of a parcel, and you have the dew point. And usually, the dew point is, well, it's always going to be cooler. The dew point generally is going to be cooler than the air, the temperature of the air, unless you're looking at a cloud or something like that. So if the temperature here is, let's say, 70 degrees, and the dew point is, 65 degrees, what that's telling me is if we cool the parcel of air down to 65 degrees or whatever, it's going to start producing visible precipitation. you'll see clouds, you'll see rain and things like that. So if the dew point, if they say temperature dew point is like 70 and 30 degrees, then we'd have to, that is indicating to me that it's relatively, dry air, and that, you'd have to cool it down quite a bit to produce any kind of precipitation or any clouds. So that's what temperature dew point is. It's probably, I didn't do a great job explaining it, but it's something you probably want to read up on. And first, because we do talk about temperature dew point, just know that the dew point, the way they describe it in the book, dew point is the point at which you get water condensing. It's going to condense into like water vapor, and also like rain or snow or something like that. Okay. And I think they talk about here if you read through the book there. So yeah, you're going to, when the temperature of the air is reduced to the dew point, the air is completely saturated. That's a term. The air becomes saturated with moisture and begins to condense out of the air in the form of fog, dew, frost, clouds, rain, or snow. So that's on the bottom of page 1213. Okay. So, yeah, they go into how they calculate, saturation points and stuff like that. It's something we don't really necessarily need to get into there. You can read on it, definitely, if you want to there. So dew and frost, those are all concerns. Frost, particularly on a wing, will actually prevent you from taking off if you have too much frost on the wings of your aircraft. So you need to be aware that could happen. So and I'll let you guys can kind of read through that. They describe it basically what happens there. If you have moisture in the air and you have a really cold surface, like the surface of a wing, metal wing, the water vapor in the air can condense into frost on the wing itself. Like I said, it'll affect, if you get any kind of frost at all on a wing, it literally destroys the airflow over the wing. And there have been a lot of incidents where pilots have taken off the frost in the wings, but the plane would not need ground effect. It would just stay in ground effect. And they won't have, going off the edge of a runway or something like that, so they can avoid that. Basically, if all fog is, this is on page 1215, fog is just basically clouds that are on the ground. So we've reached that temperature dew point, and now because of that, water condenses into fog or clouds or whatever it is. So bottom of 1215, clouds. Let's talk about clouds. So there's four different types of clouds. You have low clouds, you have middle clouds, and you have high clouds, and then you also have clouds with extensive vertical development, those like thunderstorms and things like that. Let's see those. So let's see here. So here's the different diagrams. This is a classic diagram they see in a lot of books here. You've got nimbostratus, nimbo meaning rain, stratus meaning stratified. Does everybody know what like stratus means, or stratum? It's like, straight line, basically. When you look at stratiform rocks, you see lines of rocks. We see those actually south of Barrow. I think there's some areas where there's some stratiform, like layers of rocks. It's the same in aviation. You've got, stratiform rocks and things like that. So these form of lines and stuff like that. And then you have, that's typically what we see on the ground, stratocumulus. Cumulus are usually like a little puffier. You've got altostratus. These are middle clouds, by the way. Altocumulus. So alto indicates the middle. That's the singing voice. I think alto is voice. I think anyway. But in any case, you've got altostratus, which are again very stratiform. They're very flat. And, they form larger areas. They're altocumulus. Again, are the buffy, I'm trying to say here, they're fluffy clouds. When we look up into the sky and we see those little billowing clouds, those are like the cumulus clouds. And again, alto says that, alto means that it's little clouds there. And then we have these stratus or cirrus clouds. Those are the ones that are very high. So they're typically above 20,000 feet. Don't have much of an effect on planes at all, as far as, they're not going to affect most aircraft, especially for small aircraft. We don't fly up to that altitude there. But you've got, again, cirrostratus, cirrocumulus, and cirrus clouds. And not because the air is so cold up there, it can't hold a lot of moisture. You're not going to see a lot of weather up in this area. Did you have a question?
I was gonna say that in Spanish, alto means tall.
Tall. Okay. Perfect. So, and then you've got the clouds with extensive vertical development. This is a thunderstorm. So you have towering cumulus on a hot summer day. If you look at the clouds, you'll see, actually, if you're fortunate enough to see a thunderstorm develop, it's really fascinating. But you'll actually, if you just stop where you're at and just look at the clouds, you'll actually see them rising. And that's the development of a thunderstorm. If you ever see that, like a thunderstorm that's just developing, and there, you can actually see the towering cumulus, just look at it for maybe about a minute, and you'll actually see the clouds rising. What you're seeing are the updrafts and the building of a thunderstorm. And it may just completely poop out and just it may collapse on itself, may not produce a thunderstorm. But that's how all thunderstorms start. They start with that the heating of the ground. It hits the temperature dew point, whatever converges, and essentially you've got this large convection of moisture building up in the thunderstorm itself. Let's see. So okay, and then you have what we're looking at is again the towering cumulus right down here. This is just this is where the thunderstorm starts developing, and then you've got the extensive development. This is a more of a mature thunderstorm that we're actually looking at right here. As those updrafts keep going, the storm just starts creating essentially a weather factory, and now you have this towering cumulus now. And these can reach up well into 60,000 feet. That's a really powerful storm. And there are indeed places in the weather.gov, if you go there are actually areas where you can find out the tops of thunderstorms. And that's always gives you a good idea of how powerful a thunderstorm is. So if I look at the weather charts and they say the tops of the thunderstorms are only like 20,000 feet, I'll know that those storms aren't that intense. I mean, they still produce potentially hail and stuff like that. But if I saw them next to a cell that was like 60,000 feet high with something like this, I would say, okay, I'm definitely staying away from that area because that area is producing some very intense thunderstorms. And we want to avoid something like that. So again, the degree of intensity oftentimes is tied to how high the tops of those thunderstorms. So again, low clouds, middle of the clouds, and high clouds, and then you've got your followed with extensive vertical development. Right. Yeah, they actually describe all this stuff here. Okay, a couple of terms that we need to know about when we talk about clouds. Ceilings in aviation, we always want to know what the ceiling is out there. They're talking about the ceiling of good weather. So if they say today the ceiling is at 1,000 feet, that means when I look up at the sky, I'm probably going to see an overcast layer at roughly about 1,000 feet. Or it wouldn't necessarily have to be a solid overcast. It could be broken ceiling or something like that. So in aviation terms, they're very specific when they say broken or overcast. So open or overcast is essentially you look up in the sky and you can't see any blue sky. Okay, that's an overcast. Broken can mean that like 80% of the sky is covered with cloud, but maybe 20% is you can see some blue in there, so like 20%. That's a broken. Both of those, this is important, both of those, broken and overcast, are considered ceilings, okay? Whereas, a scattered layer, for instance, where you've got a few clouds, that's not a ceiling. That's just, you've got scattered clouds. So if somebody says scattered, 8,000 feet, so you've got scattered clouds at 8,000 feet, the ceiling wouldn't be at 8,000. Now, if you have several layers of scattered clouds, they may constitute a ceiling. And get into that here in a minute here, but that becomes essentially an overcast because there's so many different layers of it. Typically, you're going to see, an overcast, just a straight overcast layer at whatever, foot, and then you just have to stay below that altitude there. There's also what we call obscurations like fog and haze. Flying in haze and hazy conditions is almost like flying in IFR. So like on those hot, humid days in the summer where there's a lot of moisture, humidity is really high. If you get up in the plane, you may notice that you can't see maybe 2 or 3 miles out in front of you. It's just white, sort of white, milky, view outside. That again, that can be really challenging to fly in because you really can't see the horizon. So we have the term called visibility, which tells us how far we can see horizontally. So if you check on the weather at Baraboo, which we can do at any time, we can look at the weather reports, and they'll give you a visibility number. They'll say like 10 miles of visibility. That's good visibility. 5 miles, a little less, not as good, but you can still go flying. 3 miles visibility is really poor. For a lot of pilots, it's not something that some pilots would call. I mean, a lot of people do, and there's nothing wrong with it if you feel comfortable flying in it. But if you're not instrument rated, to fly with just the instruments, 3 miles visibility can sometimes be a little bit too much. So again, visibility is the horizontal distance. Their ceiling is vertical to the base of the closest built-in or overcast layer. All right, precipitation, I think we know a little bit about that. We don't have to talk about that. We've got rain, we've got drizzle. Those are all things. Hail is another type of precipitation. We see hail from the production of thunderstorms as well. It'll fly out the top of the thunderstorm, and it can, hail, you may not know this, but hail can reach out like 20 miles in front of a storm. You could be actually out in a farmer's field someplace, and when a storm is passing through to the south of you or north of you, you may get struck by hail in clear skies. It does happen, and it's rare, but it does happen. So again, 20 miles away. So that's why they always say, stay away from thunderstorms. Don't.
Lightning strike clear skies.
Yeah. Mm-hmm. Yeah. If there's enough static in the air, it can happen. Yeah, like I said, thunderstorms are just weather factors, just amazing. So, okay, let's talk a little bit about fronts. Let's just make sure I come a bit along there. So, okay, yeah, let's to page 1217. Air masses are classified according to the regions where they originate. So you've got polar air masses. When I say polar, we're talking about an air mass moving from the poles, right, from the North Pole in our case. You have also maritime, which refers to oceans and stuff like that. Those are coming from bodies of water. So there's 2 types of air masses. You've got your polar continental meaning the land, and you've got your tropical or your maritime mass there. Okay. So one thing about air masses is, as an air mass moves across the Earth, it acquires the characteristics of the surrounding area. So when we so as an air mass, let's say an air mass is moving from Canada. So Canada doesn't, relative to like the Atlantic Ocean or the Pacific Ocean, Canada is not made up of a lot of water compared to the oceans, right? Okay, so the air from Canada coming down from Canada is fairly dry. So we call that polar continental. It's an air mass that is getting moved across Canada, and as it does, because Canada is dry and it's cold, it's going to acquire those characteristics, cold and dry, and that comes down. We get the cold air as it moves down from the polar areas that comes across. So again, that's what they're talking about, the air mass modification there, the characteristics is actually bringing it in. Whereas a air mass coming from the Gulf of Mexico, well, we can say that it's not continental, right? Because it's coming from the oceans. So that is a maritime mass, air mass. So that's going to actually now acquire a lot of actually, just get to this. Here we go. Yeah, so here's your maritime tropical, they call it, the maritime polar, continental polar, That's the oh gosh, it was Arctic air mass, which is followed by continental. So all these air masses as they come up. So in this case, the maritime, again, maritime referring to the water here, and T is the tropical. So it's the mid-tropics area here. As that moves up here, you've got lots of moisture. And when it hits that the continental polar mass, that dry, cold air, it condenses, and you get those thunderstorms. Either thunderstorms in the summertime, or you get these snowstorms in the wintertime. So again, depending on how strong these systems, these areas, air masses are, that dictates what's going to happen in the weather, with those those two collide. So you get typically lows from the south here, and high pressure systems from the north. And again, I encourage you to go online and look at some of the weather maps, because you'll actually see this. You'll actually be able to kind of track these and kind of prove to yourself, but yeah, that does make sense. That is going to work. Yep.
So is it possible for these two without a hurricane or anything? Is it possible for them to reach Mach 1?
Hurricane?
Like wind speeds without hurricane.
You're asking the wrong guy. I have no clue. Yeah, it's fascinating, but I honestly don't know how fast they can go.
Could happen, but it's never happened.
Yeah, I've never heard of it, but again, I don't know that much about it. I know just this much about weather right here. So, all right. So again, the air masses are going to acquire whatever terrain they're flying or they're moving over. So again, this over the oceans, it's all going to be maritime. So these are all the little M's right here indicating maritime. P stands for polar, A stands for Arctic. So again, all of the polar and Arctic air masses are going to be up here, and the tropical are going to be down here. They're going to be flowing up from the tropics upwards like this way. Does that kind of make sense? Again, you got polar, continental, and maritime. So again, this describes the type of air, or the where it's coming from. Continental, again, which would be ground, and maritime, which is water. All right, so let's see. Let's talk a little bit about symbology. So symbology for charts, we need to understand this because we're going to be reading a lot of charts, and you'll actually have to do this for the test. And by the way, I'm going to back up a second here. You don't have to know a lot about this. It's good to understand this, but for the test, they're not going to give you questions on maritime, polar, or whatever. They generally don't talk about that much, but they will talk about this. This is something you do need to know. How to read a weather map here. So warm front is always shown, not necessarily in this color, but it will. If it's a colored map, it'll be shown in red. And these are just little nubs right here that they show. And this is the direction of the map. In this case, the direction of the front here is this way for a warm front. So that's a warm front. It's showing in red. Okay, that's what it looks like, just little nubs right there. A cold front, if it's colored, it'll show it in blue, but you could show it, in black as well, which you do see a lot of charts they'll show in black. And that is the flow of this front, or the movement of this front is going to be downward like this. And it always points, the fronts always point in the direction they're moving. So the nubs are always pointing, in this case, for a warm front, they're pointing that the warm front is moving in this direction up here. Whereas this cold front right here is pointing in this direction, which means it's moving in this direction. Okay. So the way I always use just a little memory thing that helps me out, think of biting cold. Okay. And also think of blue lips. If you see a barbed line on a map and it's blue, it's probably cold, whereas red is warm. So if you want to remember that, the memory aid there, you can use that. Stationary front is interesting. You've got the little, the red nubs here on this side indicating warm front, but then you have the cold barbs on the south side indicating what's called a stationary front. That means the front is not moving. It's just stationary on the earth there. It's just not moving at all. So, and then included front we'll get into. It's not something I think we talk about much, but there are situations where you that. So that's, by the way, I'd included front is when one front, like front takes over another one on there. So let's go here. So here's a good example of a warm front right here. You can see the direction of air. So the warm front is moving in this direction right here. Let's see. Oops. I guess I'm gonna click here. Yeah, and then the warm front is moving in that direction. Okay. And these isobars, so in this case, it's kind of hard to see here because they've only got a small portion of this. But the isobars are referring to, a lower high pressure system. Here it's probably, I'm guessing, a low pressure over here. So there's probably a low here. Oops, good job drawing it out there. That would be like low pressure, and there may be isobars right here showing that. So this is typically how warm fronts will move. They'll be within like a low pressure system, but you'll have that warm front moving through that low pressure area there. All right. Cold front. This is a cross section view of colder air moving through an area there. And this is where we get thunderstorms. So some of the most powerful thunderstorms occur when you've got a fast-moving cold front. So consider this: on the warm front, or the warm side of the cold front here, you have potentially moist air, air that can hold, because it's warmer, it can hold more moisture. And then on the cold front side, you've got cold air moving through there. When the two collide, that's when you get these really strong storms. And this is kind of what we're talking about with the maritime tropical air masses hitting the continental polar masses. When they collide, this is the kind of stuff that you see. You get air. Can you guys still hear me in the back there? You can't? Okay, we'll wait till again. One second for people at home. Okay. So again, you've got cold air from the cold front hitting that warm, moist air. That's when you start seeing precipitation, thunderstorms, snowstorms, and stuff like that. This would be like coming from Canada, for instance. And as it gets closer to that warm air, that's when you start seeing some activity, some thunderstorms and whatnot. So this is an example of a cold front, and again, they've got the isobars there. You can see the isobars here. You've got cooler air at the surface, and then it's, got that cold front again. There's our little barbs there, biting cold. It's moving through the air there. You can see that, how it's going to modify the, I should say modify, is how it's going to change there's going to be definite difference between temperature here and temperature on this side. This is going to be the warmer air, and this is going to be the cold air. When those two collide, you're going to get, or some sort of precipitation or something. If the air is dry, right. Yeah. Okay. So again, if the air is, you may have a cold front move in or a warm front, but if there's not enough moisture in either of those systems, you may not get any weather at all. It may not show any kind of weather. But if there's enough moisture in the system, in one of those areas there, then that's when you might see some serious weather. So we have cold fronts and warm fronts move past us all the time, and nothing ever happens. But again, that has to do with the fact that there's just not much moisture in the air there. So, okay, so let's go here. This is an example of an occluded front. You've got a warm front or a cold front that's overtaking a warm front. And cold fronts do typically move faster than warm fronts. So this is not uncommon. This is there's the center of our low pressure system. And again, we know that low pressures move, counterclockwise. When that cold front hits that warm front, it's just going to overpass it. And that's when we get, again, the occluded front. Yeah, this is another diagram that shows the, the polar maritimes and the masses. We don't need to go through that. Let's see here. Yeah, these are occlusions, various types of occlusion. So you've got, for a frontal occlusion, you basically have three different things. You typically have a cold front here. It overtakes the warm front and it pushes any air up here. So you actually have three different areas within a cold front occlusion, and it includes the warm front there. Again, you probably won't see anything on the test on this, but you should be aware of occlusions. What an occlusion is, it's basically when a front overtakes another front. And then a warm front occlusion, you've got cold front, you've got a warm front, and because the warm front is so strong, instead of the cold front pushing under like this one right here, we can see the cold front pushes under the warm front. That's again a cold front occlusion. In this case, the warm front right here wins out, and the cold front just goes over the top of it. And both of them can produce some pretty serious weather for pilots, things that they should be aware of out there. So again, this is a stationary front. Don't get that confused with an occluded front. So again, occluded is going to look like this with both barbs on the same side, whereas a stationary front, the barbs are going to be on opposite sides. Warm front going that way and cold front going that way. Does that make sense? Okay. Right. Go here. Let's see. Cold winter. Yeah. Let's see. Yeah, you can have fronts that are tied together. In this case, you've got cold fronts typically. If it catches up to that warm front, which it oftentimes does, you're going to get that occlusion. So it usually starts out like this. You get a warm front on this side, cold front, and that low pressure is causing that anti-clockwise motion. Eventually, that cold front, catches up to the warm front and produces the occlusion. So this is a good diagram right here. This just gives you an idea of how large fronts can be. So the front is always reported at the surface of the Earth there. So if they say that there's a warm front, you may ask, well, why don't they call us a cold front if you got cold air here, a warm front here? It's because it's the direction that it's moving in. So the warm air is moving in this direction. So right here, we've got the warm front, and this is the diagram we'd actually read for this right here. So this is a really good way of understanding how these fronts work. So this is what it would look like, and this may be, at like 6,000 feet here in Indianapolis, and at St. Louis, it's down at the ground here. The clouds are down, maybe 1,000 feet. So again, this is the thing there. Trying to see there. We're going to get into METARs, reading METARs next week here. So again, another diagram showing warm air and cold air and things like that. So let's see here. Sure, we've gone through all that. Thunderstorms we've talked about. So let's just really quick, we'll talk about the different stages of the thunderstorm, and then we'll wrap this up. One other thing I want to touch on too. So the cumulus stage, let's see if I can find that. There we go. So cumulus stage of a thunderstorm is essentially when it's building. That's what I told you. If you can go out on a hot summer day when it's humid and there's thunderstorms forecast, and you see some of those puffy white clouds building, if you just stare at them, you'll see them, eventually, if you're lucky enough, you'll actually see a thunderstorm develop. And you're going to see a lot of updrafts, and you'll see it in the moisture in the clouds themselves. They'll be moving up, and in a real strong potential thunderstorm, they'll be going, up to that 40, 60,000 feet, and they'll really be developing a lot of vertical updrafts and things like that. So again, this is the building phase, this cumulus stage. That's where you're starting to build the thunderstorm. You don't know it's going to be a thunderstorm yet until you get to the mature stage. Then that's when you're starting to see lightning. You're starting to see downdrafts. So mature stage, again, it can go all the way up to like, 60,000 feet. And what you're going to have in the mature stage is all those updrafts, they're now starting to slow down as the air goes up. the air is heating, it rises, it sucks in more moisture, it gets to the top, and all of a sudden this air now starts to cool down. And when it does, you're then getting into the dissipation stage, and that's when we get all the rain and stuff like that. In the mature stage, you also see that is an area where you can see some severe downdrafts or microbursts. So that's when we talked about microbursts before, or downdrafts. That's where you start to see it, and usually it's on the leeward side of the storm. There, you're going to actually see a lot of the downdrafts, and there's just massive shafts of rain, dropping down there. So let's see. That's okay. So again, you've got cumulus stage, mature stage, cumulus or building stage, and then mature stage, and then dissipating stage. And that's basically the life cycle of a storm there. So this is, again, updrafts only. This is the building stage. Here we've got, on the mature stage where you've got mostly updrafts, lots of lightning, heavy rain, cold air, and things like that. So let's see here. Precipitation again, stuff here. Yeah, these shafts of rain can be very strong. They can, again, that's where you're going to see like microbursts and stuff like that. When you see downdrafts in a thunderstorm, that usually is the indication that it's starting to end its cycle. It's starting to dissipate as a thunderstorm. So, and also whenever you see lots of rain coming from a thunderstorm, that also means that the thunderstorm's starting to dissipate. So, here's another one. You got, wind shear. Got in a storm. There are all kinds of stuff. Just amazing. And you could have, obviously, tornadoes as well. So let's see here. All right. Turbulence, obviously we know about that. Lightning, let me see. Okay, one other thing I want to mention to you is squall line thunderstorms, and then we'll call it a day. So squall lines are essentially fast-moving areas of cold air, and you get this line of super intense thunderstorms. And whenever you hear somebody say there's a squall line thunderstorm, take it very seriously, because they are extremely violent. In aviation, you don't want to, even if you're an airliner, you don't want to be around a squall line thunderstorm, because it's just literally a line can extend, 40, 100 miles or something like that. But it's basically just an area of fast moving cold air. It hits that hot, moist air, and because of it, that reaction is really rapid. And so you get these building thunderstorms, and they produce all kinds of nasty, hail and things like that. So next time we have a really bad thunderstorm move through there, just do a little research on the TV or on the internet just to find out what caused it. And you can apply some of these things. Okay, so next week, we'll be doing weather reporting, which won't take long. And then we'll try to finish up next week. I have a feeling we're going to run over a week, which I was kind of planning anyways. And then I think the week after that, we could probably do the flights and stuff like that, which I'll let you guys know. Any questions at all? Okay. Not right now. Yeah, and I'm sure I will though in the future, because there'll be a lot of stuff set up there. So 2 weeks left. We have 2 weeks yet. Well, we have 1 week really to complete everything, the normal 1 week, and we'll try to get through all of it.
No, would you guys show me the problem?
Yeah. Yeah. Okay. Do you mind if I get this closed up here? All right. Sounds good. Thank you. Get this closed up. Oh, I gotta this closed out here. Let's see. Okay, sorry. So you had a question on.
It was this question. I think it was which landing strip. I didn't know which.
Okay, can you do me a favor? Can you email me the question or the do you know can you actually go to the quiz and as far as the grades and stuff like that, don't worry about that, because I'll take that into account that I'm not super concerned about that you guys get 100%.
Like practice tests before.
Well, yes and no. What I'll probably do is send you another website to take the practice test, and then if you just want to share your results with me, so there's a couple other ones. Like the King Schools has a free practice test you can take, And what I would do is I would go and take that test probably twice if you can. It's a lot of times it's like, it's going to take you, the first time it's probably going to take you a good 2 hours to do it. But at least what it does is it identifies what areas you're deficient in. Everybody is, I've never seen any student that has just breezed through and got everything 100% right. It just doesn't happen. So let me see here. Let me just make sure that this is, sure.